Getting started in just a few minutes here at 1:30. Good morning, and welcome to the Causal AI 2023 conference. My name is Michael Weidman. I'm sort of the MC for us today. I'll be taking us through and guiding us through all of the sessions. I'm super excited for everybody to be joining us here, both in person as well as online. We have an amazing set of speakers who have been put together throughout the day, and yeah, I'm just super excited to be learning alongside all of you about all of these advances in causality. So with that in mind, let's just dive right in here. Our first speaker is the founder and CEO of Causal Lens. He's been working in this space for at least the last 7 years or so, working to build that company up. And prior to that, he spent a fair amount of time as a quantitative researcher in the hedge fund space. So yeah, I'm just very pleased to be introducing our first speaker with his presentation on causal AI versus generative AI. Are they friends or foes? Can we just have a big round of applause for Dr. Darko Matovsky?
Thank you, Michael. Good morning. We are at a crossroad. In one direction, we see AI as the best thing that has happened to human civilization. And on the other side is AI that will profoundly damage society. We are here today because we think there is a way to bring AI to be the best thing that has happened to civilization. Thank you for being here. AI is already causing a lot of harm. This is an example of Zillow's AI going crazy, creating 304 million operating losses and 2,000 jobs lost overnight. Why? Facebook Prophet did not understand causality. It was simply fitting a curve to the data without understanding the cause and effect relationships. Here's another example of AI causing harm in society. There was an algorithm that was used by major insurance companies and major hospitals that was biased towards black people. Why was this? Because the algorithm picked up a spurious correlation between health costs and health needs. There is more. Actually, the internet is littered with examples of AI causing harm in society. This was Amazon's AI tool that shows bias against women. Over time, it learned that anything that had woman inside was not a preferred CV. Even when a woman was the captain of the chess club, that was discriminated against. More recently, Cigna was sued over the algorithm that allegedly was used to deny coverage to hundreds of thousands of patients. We had a more recent example where lawyers used ChatGPT to build a defense, and it turned out that they were citing imaginary case law in court. So current AI is already causing a lot of harm. And we really have three options. Option one is ban AI altogether. Who here would like to ban AI altogether? Okay, no one. We can heavily regulate AI. Who here would like to heavily regulate AI? Maybe one or two people. A little bit of regulation, yeah, that works. And we have option three, which is use better science to build safe AI. And how many people here would like to use or build better science? Okay, great. You're in the right room. And this is why our community is growing so fast. This is why Causal AI is growing so fast, because we're all passionate about the potential that AI can bring to society. We just need to make this technology safer. We need to understand how it works. We need to understand the cause and effect of every algorithm we put there in the real world. We want to make AI great again, and causal AI is the way to do it. Well, okay, really, we want to make AI safe again, but I think that's what we all hear today, and thank you so much for being part of this exponentially growing community. I want to show you an example. This is a real example that we did with a major financial institution, just to show you the power of causality and looking, having a unified language that humans and machine can speak. As most of you probably know here, this is a causal diagram. It's a bit of a simplified one just to illustrate the point, but it is from a real example. So this major financial institution was building an algorithm to decide automatically who to provide loan to. So it was an algorithm to help them decide whether to provide a loan or not. And they threw a lot of features, and they realized that postcode was the highest correlated feature to whether someone should be giving a loan. But they also saw that race and income are correlated, but they're like, okay, race we cannot use, of course, so let's throw that aside. But income seems like a fair game. If someone earns more, they should get a high loan. And so they put income and postcode, and they shipped it to the model review board. The lawyers came back and said, we are really a bit concerned that you have a racial bias in this algorithm. We've done some tests. The team went back and said, well, let's build a causal model to try to understand this. What they learned by building a causal model was that postcode and race were correlated, and having postcode in the model, although it doesn't seem, seems benign, it's actually quite dangerous, because it's hiding race in the information, right? Certain people live in certain postcodes. And so with the power of causal diagrams, they were able to remove this bias and said, okay, we cannot have postcode because that's hiding race, and therefore decided to use just income and other variables that they were able to quantify that they're not biased. And with the causal model, they were able to do something even more powerful. Not only they were able to explain to their customers why their loan was rejected, but they were able to tell them how they can be accepted in the future. They were able to tell them that if you increase your income by just 10%, we'll absolutely be able to lend you this for your dream house or for your dream kitchen. So not only, with the causal model, this financial institution was able to create trust with their customers. It was able to explain them exactly why the AI said you can't have it, and it was able to tell them exactly what they need to do in order to qualify for it. And that is the power of causal AI in practice. There was a great article in Nature which spoke about why artificial intelligence needs to understand consequences. And they went ahead and said that machines that grasp cause and effect can learn like humans through imagination and through regret. So our community is growing exponentially. So I decided to ask ChatGPT why causal AI is better. And it gave me surprisingly good answers. I couldn't agree more with it. The community is growing so fast, and the need for this technology is growing so fast because we want robust AI. We want the AI to generalize beyond training data. We want to decouple ourselves from historical patterns. We want to do counterfactual reasoning, kind of like similar to what I showed earlier. Things that are counter to the fact, by definition, are not going to be in observational data. We want to have fair and bias-free AI in our society, and I showed you an example for that. We want to be able to fully explain the AI and so on. So I thought this was a really nice summary of why our community is growing so fast and why we're all excited about bringing this technology in the real world. We have come a long way as a community. This is how, if you Googled causal AI in 2017, this is what you would have seen. It was us and Elias, who is a student or now collaborator of Judea Pearl. We were the only two people in the whole world talking about causal AI. If you were to repeat this Google search today, very different world. You'll see all the big tech, you'll see all sorts of large corporations incorporating causal AI. We've come a long way over the last years. And we're only accelerating. If you look at the number of newspapers, so top machine learning conference, we've seen yet another extrapolation of the exponential trend happening this year as well. We've seen huge investments from big tech in this technology. Microsoft and Amazon actually collaborated for the first time, as far as I'm aware, on an open source project specifically on the topic of causal AI. Causal AI is now on a bunch of Gartner hype cycles, and what's interesting between last year and this year is that last year it was a technology that was going to be adopted or predicted to be adopted in the next 5 to 10 years. In just a year, that horizon has changed from 5 to 10 to 2 to 5. So we've brought causal AI forward, and that's really exciting. We've also seen actually the EU regulation coming out and mentioning causal understanding as a key to safe deployment of AI in high-risk situations, much like the one I showed you earlier with the loan applications. That all is likely to be covered by the new regulations, and you can only have those models in production making decisions for real human beings if we can explain the cause and effect that goes behind that decision. In the last 12 months, we've also seen correlation being cancelled on Twitter for impersonating causality. So that's great. In the last 12 months, we've also seen exponential growth in generative AI. On the chart here on my right, you'll see the exponential growth in funding in Gen AI. On my left, you'll see that supposedly Gen AI will break the data centers. There's a prediction that there will be 76 billion of compute by 2028. So Gen AI is also exploding. Causal AI and Gen AI have been the two most exciting technologies and the fastest growing AI technologies over the last 12 months. And that is great. Now, both Gen AI and Causal AI, are not AGI, right? They're not perfect for all use cases, but they all have, great strengths and great, some weaknesses. Here, I wanted to show you some of the weaknesses of Gen AI. This is a very simple, math that you could do on your calculator, but LLMs are struggling to do that out of the box, without invoking additional libraries and writing additional code. So that's one area where the generative AI or the LLM specifically have failed, is doing basic mathematical computations. They don't seem to do very well with logic and reasoning. So if Mike's mom has 4 kids and 3 of them are Louis, Drake, and Matilda, what is the name of the 4th kid? For a human, it takes like 3 seconds, we're done. For a language model that predicts the next word, this is a very tricky question. If you ask a Gen AI that generates images to build a salmon swimming down the river, you will get something that looks like this. There was a really interesting paper from Meta, ETH Zurich, University of Michigan, that asked a simple question. Can large language models infer causation from correlation? And the answer was basically no. They performed close to random on this task. So Gen AI is great. It has amazing use cases. But it cannot be used for logic, reasoning, computations, and use cases where we cannot tolerate hallucinations. But what if there was a way to combine the best of these two emerging and fast-growing technologies? What if there was a way to put causal AI and Gen AI together? What if we can find a way to get these technologies to play to their strengths? Maybe we can achieve 1 + 1 = 3. And I know the math is not right, but LLMs don't seem to care, so I thought I'll just put it there to illustrate the point. This is a real example, a real story that I heard from a CIO of a Fortune 100 organization. It's a tale of two teams. The first team decided to solve the use case just using LLMs. The second team decided to solve the use case by using LLMs and causal AI. So let's see how the results went with the first. I've taken out all the sensitive stuff here, so I can show you this. But this is how the conversation went with the team that used just as LLMs. So you can ask it, what is driving our customer retention? This was a retail example. And the LLM would say, well, the length of time the customer waits as a checkout. Seems like a very, very, very good answer. So great, that's awesome. But we want to know exactly how much. So we asked the LLM, can you quantify it for me? And then LLM can do things like, there's an inverse relationship between the wait and retention. And you can kind of see how this works because you may be able to find some academic papers that have figured out this relationship. So that's great, but it doesn't quite tell us by how much. So if we start asking the more interesting questions, like what should we do to increase the lifetime value of our customers, it tells us again something very sensible. Increase the number of staff at the checkout. But is it increasing it by 20%, by 50%? We don't know. It's a very intelligent answer, and it's correct, but we don't know by how much. And so when you dig deeper and you say, hey, tell me by how much, the LLM say, well, I can't quite compute that, but maybe if you give me some sort of a plugin, I might be able to write some code or invoke some algorithms. And so it was success, but they didn't quite solve the business problem. Let's see how the LLM plus causal AI team did. They had the same challenge. They asked the LLMs, so in this case you had LLM as an interface, so as a user interface, and then you had causal models underneath. So the LLMs were essentially the prompts were generating code that queries the proper causal model. So that's kind of how this looked like. And so we went through the same again. Okay, what is driving a customer retention? Same answer, great. But can you quantify it for me? And this is where the magic started happening, because now the LLM was not making things up. It was now writing code to query the causal models underneath. And it was able to say that for each 5 minutes of additional wait, the LTV decreases by 20% over a 1-month period. So that's very specific. That's really great. And a typical customer spends $100 a month, and if you don't do anything, they're going to spend $80. That's going to have a huge impact on your business. Natural question is, how do we fix this? What can we do to fix this? And the answer is that they need to increase the number of checkout staff by 13% in a bunch of stores and 17% at some other stores. Now we know what to do. Now we know how to make the business better, and we can trust this because it's been derived from causal models that were built by human and machine working together. So today I want to show you the world's first example of combining LLMs and causal AI. So I'll show you quick snippets of how this looks like in the real world, so you guys can so you don't have to imagine it. So here is an example of very similar. What are drivers of churn? We have a causal model that has a causal diagram. This is invoking the causal diagram. We can see exactly how this works. So we're using the LLM as a user interface, but we're actually querying real causal models that were built by human and machine together. We're then able to do cool things like explain a very complex causal model to an analyst, to a human, exactly what are the mathematical functions that are between these edges. So we are, again, using this wonderful technology of Gen AI to help us explain something that is quite sophisticated on the modeling side. We can query the causal models to ask for, what are the top 10 customers that are going to churn. It's a great way for the humans to interface with the machine. Again, we're querying the causal models and we're getting a bunch of answers. This is also, I think, a great use of Gen AI, where we want to actually take the action in the real world. Maybe we need to write an email, generate automatically an email to actually action our recommendation or our decision. In this case, sending an email to a customer automatically that they qualify for 16% discount that will prevent them from leaving the service. So this is the world's first combination of causal AI and Gen AI, and we think this is going to pave the future of decision-making in the enterprise. In fact, we're not the only ones that think this. Databricks and .IQ ran a big survey of 400 AI professionals, and they asked them, what technology are you going to adopt next year? Causal AI scored #1 of not using right now, but have plans for next year. So we think that this synergy of causal AI and LLMs in particular are going to be the future of decision making. So if you had access to technology that allowed you to combine these two technologies, what use cases would you use them for to transform your organization? We can talk about this later. And before I wrap, I want to give you the heads up for something very exciting happening today. This is the last piece of the decision-making puzzle. We're launching Decision Ops today. And I'm not going to reveal too much because Tom will do a great job later unveiling this new capability. But in summary, we have taken model ops to a whole new level. We've taken model ops that simply measures model performance and tracks that to decision ops that can actually quantify the effect your decision-making systems are having on the ROIs that matter to your organization. And this is the last piece of the decision-making puzzle, and we're so excited to unveil it this afternoon, and Tom will tell you all about it and show you some cool, exciting demos. So do tune in for that. Thank you so much, and have a wonderful conference.
Thank you very much, Darko. Well, that was a great talk right there, and I especially enjoyed seeing how there's these potential connections, and it's not just a zero-sum game between, causal AI and all of these generative techniques that are occupying so much of the media attention these days. The other thing that I especially enjoyed about that talk is that there was a bit of foreshadowing for some of the upcoming talks that are coming. So Darko was just mentioning Tom, who's one of our final speakers today. Very much looking forward to that. And for those of you who had very sharp eyes, you may have seen that there was hints of our very next speaker, who I'm very excited to introduce right here. So yes, our next speaker here is coming to us by way of academia. So he has degrees from Erasmus University and Brown University. And then he has been spending a great deal of time as a professor at Harvard, as well as currently at Stanford University. Perhaps he's best known around here for being part of the 2021 Nobel Prize in Economic Sciences, which he shared for his methodological contributions to the analysis of causal relationships. So here to tell us a bit more about that, and in particular to speak more about challenges in causality, combining experimental and observational studies, it's my great pleasure to introduce Professor Guido Imbens. So thank you very much.
Thanks very much. Thanks for the very kind introduction, and thanks for having me here today. When David Cart, Josh Engers, and I received the Nobel Prize, that day NPR actually announced that Josh and my part of that prize was for a study of causal relationships, which greatly surprised our spouses. So listening to Darko's talk, actually, I was reminded of a paper I was reading yesterday when I was on the plane. There's a study it was an experiment that was done at the Boston Consulting Group, where they were looking at the effect of AI on productivity. So they did an experiment where they had a number of teams work on some problems, and some of them were given ChatGPT to kind of help them look at the problem. And for a whole bunch of problems, that greatly improved the productivity. And one of the interesting things was that it actually improved the productivity more for the inexperienced teams. It seemed to help them kind of compensate for the lack of experience relative to some of the other teams. And there's a lot of other examples now where it's sort of clear that AI can really help the productivity. I think this work kind of looking at the effect on call centers, you kind of see the same thing, that overall it helps a lot with the productivity, but it particularly helps less experienced workers catch up faster. Actually, in an MBA class I was teaching last quarter, at some point we had an exercise where the students were supposed to write a prompt soliciting charitable donations. This was embedded in some other experiment where they did a survey. We were compensating these people, and then at the end they were giving a bonus, and the students were asked to write this prompt to get the people to donate the bonus to some charity. And again, we also compare that to a ChatGPT generated prompt, which did much better than most of the Stanford MBA students' prompts there. But what was particularly kind of interesting in the study at the Boston Consulting Group, that actually for some tasks, the AI made the teams do worse, kind of when they were particularly complex tasks outside the frontier. The AI actually lowered the productivity, and had particular difficulty kind of in helping people make better recommendations, make better decisions. And what's particularly interesting, what's sort of relevant here for what I want to talk about, was that these complex tasks kind of had the feature that people had to combine information from relatively disparate sources, and so they had to combine these pieces of information which were somewhat contradictory, and they had to kind of figure out a framework for embedding these pieces of information that made sense and that led to good decisions. And so what I want to talk about here in general kind of is combining different sources of information. And so what I want to look at, and I'm going to make it kind of more narrow, but so I want to look at combining experimental data with observational data, where these two have very different strengths and weaknesses. Observational data is often very rich in detail. There's often a huge amount of it, It's great in terms of representativeness of the population, but often we're not really sure whether we can get the causal information out of that, because there may be a lot of unobserved influences going on, and so we may be able to get a lot of correlations very accurately from those data, but we may not be able to tell whether these correlations really reflect causal effects of the type that we need for the decision making we're trying to do. And so at the same time, experimental data are very good in terms of internal validity. If we actually do a well-run experiment, and kind of there the well-run is a very important caveat. It's very hard to do experiments well. There's a lot of complications. We've studied how to do experiments kind of since the 1920s, but that was often in very simple, stylized settings of the type kind of that are still very common in medical settings. You give some people a new drug, some people not. You kind of keep them separate. There's no interactions between them, and you compare outcomes. But now often we do experimentation in much more complex settings where units interact in very complicated and strategic ways that makes even doing experimentation very challenging. But leaving that aside for the moment, if we do have well-run experiments, we can often get very good answers to very specific, very narrow questions, but often they're limited in terms of the richness of the data, in terms of the background characteristics, meaning that we can only get limited information about heterogeneity. We may not be sure that the experimental population is really comparable to the target population. So we may get good answers for very specific questions, but they're still not perfect for the overall questions we're interested in. And so what we want to do here is look at ways of systematically combining observational and experimental data in a way that allows us to answer questions well that neither of these two types of data can answer on their own very well, or to improve the questions that one of them could answer on its own. And so having methods for that will make experiments more valuable by extending their value beyond kind of the narrow things that they were designed for, and it'll make the observational data, of which we typically have a huge amount, more valuable by making sure they're grounded, that they actually give us the right answers to the questions where we know the right answers. And so here I'm going to look at two specific cases. There are two different papers. One is with Susan Athey, who was also at Stanford, and Raj Chetty, who was at Stanford for a while, who's now back at Harvard. And the second paper is also with Hyun-Sung Khan, who's at the University of Wisconsin. So in the first case, we're looking at two data sets, where one experimental, one observational, where the observational sample has richer data, has data on the outcomes we're actually really interested in. And the experiment is limited in that it only has information on a subset of the outcomes and not the outcomes of primary interest. And we're going to see how but we're worried with the observational data that there's biases present there, and we're going to try to figure out ways of using the experimental data to get rid of these biases and get better answers to what the observational data on its own would deliver. Second problem is slightly different, where in the observational data we don't actually even have the treatment we're interested in. We just have a subset of we have some of the variables that are in the experiment, plus some additional ones. And again, we'll see that can be very valuable in allowing us to make better decisions faster. So here's kind of example we have in the paper for the first setting. The fundamental question we're interested in is about the effect of a particular educational intervention. Here it's having small classes. We think small classes probably improve the experience for students, and there's some evidence that it improves test scores early on, because that's not really what we're interested in. We don't really care about test scores. We want to see what the long-term implications of these interventions are. Long-term labor market outcomes, ideally, or long-term educational outcomes. And similarly, in many other settings, private companies do experiments. They may observe a bunch of initial outcomes, but really what they're interested in are long-term value measures of engagement of the customers in some form or another. And so here we have two data sets. One is from a famous experiment that was done in Tennessee, where they randomly assigned students to big or small classes. And we see here looking at third grade test scores, we see that the test scores improved markedly for the kids in the small classes. Not surprisingly. Kind of these kids were in smaller classes, they got more attention, they did better on the same scores. They were randomly assigned to these classes, so it's very plausible that this gives us a good estimate of what the causal effect of these small classes is. But suppose what we're actually interested in is not just third grade test scores, but we want to know what it does over the long run. Maybe that just kind of is a very temporary effect and it just wears off, and after a couple of years it didn't actually make any difference whether they initially were in these small or big classes. So we have the second data set from New York that is not an experimental. Their kids were not randomly assigned, they ended up in bigger or smaller classes. And there what we see is quite different. Even in the third grade, we see that the kids in the small classes do worse in terms of the test scores than the kids in the big classes. It's statistically very significant. It's very precisely estimated because this was a big observational sample, as we often see in with these observational data. But it's very negative. So if we take this at face value, it would suggest that being in small classes in New York is actually a really bad thing. Now, that doesn't seem very plausible. Does it? It seems much more likely that there was selection going on, that somehow the kids who ended up in the small classes were different from the kids who were in the bigger classes. And so that this is not the minus 0.118 is not an estimate of the true causal, not a good estimate of the true causal effect. And so we see the same for the 8th grade test scores, where we get a negative effect. It's very precisely estimated, but if we're just interested in the effect on 8th grade scores, what do we do now? We have this experimental estimate for this for Tennessee, for the 3rd grade test scores for a different outcome that is big and positive and precisely estimated. But in Tennessee, we don't know anything about what happens in 8th grade. And in New York, we see this big negative effect. But we're kind of worried about that because we see the minus 0.118. And so we don't really trust the minus 0.118. And as a result, we don't really trust the minus 0.138 for the 8th grade either. So the problem we're trying we're studying here in this works, how can we actually combine these? How can we take some of the insights we get from the experimental data and help us improve the estimates for the observational data? And so what we're going to do, kind of the structure we're going to set up. And so here I'm doing this in a causal diagram form, and it's in the paper and some of the slides have other versions of the key assumptions. But really the key assumption we're going to make is that there's some unobserved confounder, something that's creating biases in the observational data. That means that we can't simply look at the comparison between big and small classes in New York, and interpret that as a causal effect. There's some unobserved confounder there, but the key assumption is that that's the same for the 3rd grade and for the 8th grade test scores. It's not that there's kind of a whole bunch of these different unobserved confounders floating around. There's a key thing that is different between these kids that are in the big classes and the small classes, and that means they're going to do better or worse, and that's kind of stable between 3rd and 8th grade scores, between these different outcomes. And so in the experimental data, the link between that unobserved confounder and the classroom size, of course, is broken, is eliminated because of their experimental assignment. And then what we can do is combine these data sets and figure out what the bias is we're getting in the observational data, and then use that to adjust our estimates for the 8th grade scores. And so, again, kind of to summarize it, we see in New York the estimate for the 8th grade. We don't really believe that, because we see that the estimate for the 3rd grade is so different between New York and Tennessee. Now, that could be different because the populations are very different in New York and Tennessee, and we'll do some adjustment for that. But in the end, we believe that the reason that we see such a big difference is because there's selection in New York, because it wasn't randomized, and we're going to exploit that difference between New York and Tennessee to adjust the 8th grade estimates. Now, we could do a very simple thing. We could just say, well, there's this difference between New York and Tennessee in 3rd grade test scores, and that would have been the same in 8th grade test scores, and we can therefore just use that adjustment to get an estimate for what it would be, what the adjusted estimate would be in New York. That's kind of a very naive thing, and that would rely on the primary and the secondary outcome really being measured on the same scale and being kind of similar in nature, and it only being a scalar. But so what we're going to do is do a more systematic way of using a bunch of initial short-term outcomes to figure out what the biases are in the observational study, and then use that to adjust the estimates for the primary thing we're interested in. And so kind of to see what that looks like. So here again, I have the same table as before. In 3rd grade in New York, we had the estimate, it's kind of the difference in mean with some adjustment for background characteristics of these kids. That's not really of the essence here. We have this short-term estimate of minus 0.138. Then we built this model that takes the experimental data for the 3rd grade and adjusts the 3rd grade estimates for New York. It adjusts it in a way that it forces that estimate for 3rd grade in New York to change from minus 0.138 to exactly the same number as it is in Tennessee, the 0.201. So I'm going to create this transformation that gets us back to the Project STAR Tennessee estimates for 3rd grade, the 0.201. The fact that these two numbers are the same is by construction, the procedure is going to deliver that. But then we can apply that same procedure to the 8th grade test scores that we don't see in Tennessee. And now that adjusted estimate is 0.057. That seems a much more reasonable estimate. Now that's positive as well. And so that looks like a plausible estimate of what the causal effect in New York could be on 8th grade test scores. Now, of course, that's all nice and well, but does this actually work? How much can we actually trust this? Daka was talking a lot about trust early on. And so the procedure, and I can go into the detail, and I can put up a lot of equations kind of showing exactly what we're doing, but how credible is this? How much do we actually believe that this is working? Well, so here we can actually test that because what I was saying earlier wasn't quite true. In other words, I lied. We do actually have 8th grade test scores for Tennessee. So we do actually know what the truth is, or at least what the experimental estimate is for Tennessee. We didn't use it in creating this table, but now we can go back to the Tennessee data and look at the 8th grade test scores and see what the actual causal effect was of having a small class early on 8th grade test scores. And so what you see is that it's quite close to our estimates. So here we can actually validate what these procedures are doing. They're taking kind of these 3rd grade data in Tennessee, they're taking the 3rd grade data in New York to build this adjustment. We then apply that to the 8th grade outcomes. We get this adjusted estimate, and actually it's pretty close to the experimental estimates in Tennessee. And in fact, kind of we do that more systematically. We have a bunch of additional test scores, and even for high school graduation rate, if you look at the raw estimates, that suggests that there's a negative effect of small classes on high school graduation rates in New York. If you look at the adjusted estimate, you're back to a positive and statistically significant estimate comparable to what you get in Tennessee. So here, kind of using these observational data, even though there's huge biases in the beginning, it's not just that the numbers are a little different, the sign is completely different. We get this big negative effect. Grounding these observational estimates with some experimental truth, even for a limited set of outcomes, can then create models that are much more stable and robust and give us credible causal estimates for a wide range of outcomes by kind of just eliminating the bias in particular, so the key biases in particular components. And that's kind of what we're trying to do here. And so the bigger picture here is that you may have these big causal models that have a lot of components. Some of them you may be more confident about than others, but having some experiments, having some targeted experiments can really help you make sure that the model is nailed down, is grounded in reality for key components of that model, so that the conclusions and the implications for making decisions are going to be more credible and more robust. So now let me go into some of the detail, kind of see where this relates to some of the literature. So what we're looking at here, and soon I'm going to switch to the second problem, so I'll give a couple more slides here on this problem. So here we're looking at a setting where we have an experimental sample for which we see the treatment we're interested in this case, small versus big classes. We may see some pre-treatment variables, some background characteristics. We see the secondary outcome, but we're not really interested in that. We're interested in the causal effect on some primary outcome, which we do not see in the experimental sample. In addition, we have an observational data set where we see everything. We see the treatment, we see the primary outcome, we see the secondary outcome, as well as the pre-treatment variables, but we're worried about the fact that there's unobserved confounders, that there's biases in the comparisons between the treated and the control units, and so we don't trust the results based on just the observational sample, but we can't rely just on the experimental sample because we don't see the primary outcome there. Now, we're going to assume, and that's essentially definitional, that in the experimental sample we have internal validity, that we can estimate the things we're interested in. And we can adjust for observed confounders. That's not an issue here, but we're confident we get causal estimates out of the experimental sample. We're assuming that we have external validity in the sense that in the end, the populations in the experimental and observational sample are comparable, so that we can actually use the Tennessee Project STAR data to learn something about the New York data. Again, we need to do something like that if we think these populations are completely different. There's nothing we can learn from the Tennessee data about the New York estimates. So the content of this assumption really is the notion that what we see in the third grade in New York relative to the third grade in Tennessee is not coming from the populations being different. It's coming from the selection into the treatment being different, from the fact that the observational sample in New York, the small class kids were not comparable to the big class kids in New York. Now, what we don't want to assume is that we can just do things in New York. It's just using the New York data. We're not willing to assume that there's no unobserved confounders. We think that the differences are too big, that the selection problems are too large. And so what we're going to assume, the critical assumption is that whatever this unobserved confounder is in New York, it's the same. There's a single one that drives the differences both for third grade and eighth grade. And so that's really the critical piece, and that's a strong assumption that's saying that whatever biases there are in eighth grade are the same. They're not the same magnitude, but they're the same variables. They're the same underlying biases as there are in third grade. And so by enforcing an adjustment that gets us back to the Tennessee results for third grade, we can adjust for the eighth grade comparisons as well. Now, I'm running low on time because I want to leave some time for questions. So let me, so here's the kind of technical form of that assumption. Whatever biases there are, after we condition on third grade outcomes, we would be able to get rid of these biases. Then, given that set of assumptions, it turns out we can estimate the effect on eighth grade doing this adjustment, and we get these estimates that I showed earlier. Let me now actually just move to the second example, because I want to show some of the results for that second problem. So the second problem is slightly different in that for the observational sample, we don't see the treatment, we just see the primary outcomes, the secondary outcomes, and any pre-treatment variables. And so this is a setting that's sort of very common in a number of different literatures. Originally, where some of the terminology comes from, this is in medical settings. If you do experiments for, say, cancer drugs, the primary outcome we're often interested in is something like mortality. That takes a long time to observe, and so we can't run these trials for long enough to get precise estimates on the effect of mortality. So instead, we look at intermediate measures, at surrogates, at things we think mediate the effect of the drug on mortality. And so they could be things like tumor size. And so we do an experiment where we look at the effect on these intermediate outcomes on tumor size, and then we say, well, if the tumor size goes down, we know that's associated with lower mortality, and so that's a good enough outcome for the trial. So here we want to do that a little bit more systematically, and we want to do that in a setting where we may have lots of intermediate measures. And so kind of a common use case is that a company does some experiment. They want to make a decision about the intervention within a month or within a couple of weeks, but really the primary outcome is the long-term value of the customers as a result of that intervention. And that's something that would take a couple of years to materialize, to measure, but they want to make a decision now. And so what we're going to do here is build a model for the relationship between all these intermediate measures you may be able to record early on, and there may be a whole set of 10, 20 different measures. We build a model that relates that to the long-term outcome. We do an experiment where we measure these short-term outcomes, and then we combine that with that model to predict the effects on the long-term outcome. And again, I'm going to illustrate that using some data here. Here, this was an experiment for a labor market program for people for long-term unemployed individuals in California. So we actually have data where we see outcomes for a long period afterwards, for 9 years. We're going to use the first 6 quarters, the first year and a half after the experimental intervention as surrogates, as initial measures. We build a model relating that to outcomes for the 36 quarters, and then we see how well we predict the outcome over 36 quarters. So we actually have a data set where they did the experiment at different locations. So we pick one location, Riverside, as the experimental sample. We pick the other locations as the observational sample. And so actually, so here, let me get to the key slide here. Is it, sorry, let me, actually it looks like I left out that, that slide, so let me just stay here for a second. So what we see is if we take the data from the experiment for the first 6 quarters, if we look at just a simple average outcome for that first 6 quarters, we get an estimate of an improvement in employment rates of 10%. The actual value for the experiment over 36 quarters was much lower, was 6%. But if we combine the observational data that relates these early outcomes to the long-term outcome, we get back to about 6% after 6 quarters. So it turns out that here, doing the experiment just for 6 quarters would allow you to estimate the long-term effect credibly and precisely without having to actually run the experiment for 9 years, which obviously would not be very useful because too many things would have changed for that decision to still be relevant. So let me pause here to leave some time for questions. But kind of the bottom line here in this project is, in many cases, we have very rich observational data. We collect that all the time in ways that clearly has a huge amount of value, has a huge amount of information. But it has also drawbacks, that it's very hard to directly draw causal inferences from the observational data, because there's all sorts of biases in there. Experimental data has the great advantage of answering these very narrow questions very well, very credibly, and by combining them, we can leverage the strength of both and build better models, safer models, and more robust models for decision making. Thanks.
Thank you very much, Professor Inman. Yeah, really fascinating talk right there. Just going from some of my own experiences in the past, whenever you were speaking about, for example, difference in differences. That was a technique that, yeah, I've used many times in past lives, but always felt like an inelegant tool for addressing the issue. And it's good to know that there is a better way out there now. Really fascinating talk. Thank you. We are open for questions. If anybody would like to ask any questions, just raise your hand and make yourselves known, and Zoe will be able to come around with the microphone to let you ask. So is anybody bold enough to ask the first question of the day? We've got one right there.
Hi, Guido. I'm actually a student, from Stanford. Could you do the other direction of estimation? So tech companies are always interested in doing an experimental study in a small sample and then adjusting estimates in like large samples. So in the previous setup, I would be interested in thinking about how I might estimate correctly the results in the non-randomized sample. So you showed the other way, but I'm wondering for this direction.
Yeah, you can go both ways there. You can get the estimates for the experimental sample or the estimates for the observational sample. In the end, the assumptions we're making allow you to go back and forth between the two samples. So that's not a fundamental problem. It sort of makes the estimation slightly more complex, but not in a fundamental way.
Great, thank you. And I know that there is questions coming in from online. So for those of you who are joining us on the live stream, feel free to ask questions via that, and you will be heard. So one question coming in from online.
Thanks, Michael. Thanks a lot, Guido. Fantastic talk. So we have a question from Alex Molak from our live stream. Does the method presented for the two schools guarantee causal identification?
No, so in the end, we are making assumptions here about the causal structure. And so the key thing is that we're assuming that we're making two key assumptions. One is that these populations, after some adjustment, are comparable. So it may well be that the ethnic composition is different in Tennessee versus New York. The income distribution may be different. There's lots of things that we allow for. As long as we observe them, we can adjust for them. But we make fundamentally an assumption that similar kids in Tennessee and similar kids in New York would experience the same average, the same distribution of causal effects of these interventions. That's one thing. The second thing is that we're assuming that whatever these biases are for these different outcomes here, third grade and eighth grade, are driven by the same unobserved confounders. And we can relax that a little bit by having more initial outcomes. And so if instead of just looking at one single test score, we look separately at mathematics test scores and reading test scores, we can build a richer model for the unobserved confounders. But things are limited there. We do need to make some assumptions. And that's why it's very important, why it's crucial really to build ways of validating these models. And so here, by having these, here we validated it because we actually had the 8th grade scores. And so we can validate it also on 4th, 5th, 6th grade scores. And so you build confidence that these methods that rely somewhat on the randomization, but somewhat on maintained assumptions that are not driven by the design, that those are credible. And so it's key to kind of do analysis that validate these things rather than just building these things and then saying, well, it looks like it's working. The validation is really a key feature of these strategies.
Thank you so much.
Great.
In the context of heterogeneous treatment effects, how important is the covariate distribution in the experimental data? Must that match in the observational data?
Yeah, so kind of I left that out of the talk, but clearly we have some background characteristics and they're quite different in Tennessee and New York, and we adjust for those. In principle, we're not making any assumptions on that limits, that restricts the heterogeneity of the causal effects. So we could do this by also looking at subgroups. We could build models that explicitly look for heterogeneity, whether these small class size effects are more important for low-income kids or for high-income kids, kind of where in the distribution they matter. They could matter more for kids who would otherwise be at the low end of the grade of the test score distribution or the high end. So there's all sorts of heterogeneity that clearly would be very important to understand in terms of the substantive decision making, how you would choose these class size distributions. And the model doesn't at the moment put any structure on that, so we can estimate these things with sufficiently rich data.
Hi. In either of these case studies, was it possible for you to identify the unobserved confounders at the end? And if so, what were they?
Sorry, was it
possible for you to identify the unobserved confounders at the end?
Yeah, so in the end, kind of the assumption that sort of in this case, with a single secondary outcome, that this unobserved confounder was the same, means we can actually extract that by comparing the experimental and the observational data. So we can actually, there's some normalization involved there because the scale is obviously not identified, but you can see what it is, what it's correlated with, and you can see how where in the distribution of outcomes so what it's correlated with. So there's in principle a lot you can learn about the selection process by doing so.
Thank you, Dr. Imbens. So I see we have experiment group and observational group. There can be a time period between the experiment and observation happen. So between this time period, it's quite likely that we have some event that have known or unknown impact on the observational group. So when this happens, do we always have a message to make an adjustment, or in what condition we can decide the experiment is not useful and we need to run new experiment?
Yeah, no, that's a very good point. Because in practice, these things are, of course, always very complicated. Even here with this Project STAR and New York data, these were not from exactly the same years, but you would think that the educational production function in general is sort of reasonably stable. Now, of course, the last couple of years, it wasn't very stable. Kind of during the pandemic, things changed so much, so that it's clear if the observational data came from the pandemic years and the experiment was pre-pandemic, you wouldn't really think that combining those data would make a lot of sense, because it's not just that there's a simple adjustment that would make these things comparable, but you would think that all the relationships changed. So exactly when you can do that, of course, it's tricky, but that's true in general. We do want to build these models that are stable over time. Even when we do experiments in the past to make decisions about the future. So that only makes sense if we think there's some stability, that some of these causal relationships do stay stable, and that informs the way we do the modeling. But if you think about a sort of international company doing experiments in different countries, if you're looking, say, at the effect of prices on sales, you wouldn't look at the effect of, say, a €1 increase in price and then look at the effect of a $1 increase in price. You would look at relative changes and look at price elasticities, because you think they would be more stable across different locations and across different time periods. So you try to build these models that have relatively stable parameters across different locations and different time periods. But exactly how to do that is going to be partly context specific, because in medical settings, we think that a lot of the medical interventions are very stable. Kind of you try a drug out in Europe or Latin America or Africa or Asia, that's probably not that different from doing it here in the US. But for some interventions, that can make a big difference. And so we do need to use some subject matter knowledge there to get a sense of how stable we think these effects are.
Hi, Guido. When it comes to the conditional external validity that we clearly need in these methodologies to port, let's say, the experimental results over your observational sample, how about the time dimension, so the stationarity of these? How likely it is that we can, the change in results in the observational studies from the 3rd and the 8th grade are the same, evolves the same also in the experimental studies? And so how likely it is that we can assume that the evolution in time of the experimental results is similar? And are there ways that we can use, maybe using predictions to try to infer, and predict, the evolution of this relationship, how it evolves in times in the two different settings?
Yeah, so I mean, a part of that involves, again, thinking about the subject matter knowledge, kind of how do you think these interventions affect things? You do think that if having small class sizes early on, if we're interested in what that does long term, it better show up sometime early on in the test scores. If you don't see it there, it seems very implausible that it would have some long-term effects. And so what you want to do is build a model that takes account of that and that tracks the evolution of that over time. And so doing that here, kind of by looking at all these intermediate the test scores, is sort of one natural way of doing that. Now, it may well be that part of the intervention affects other things. It may make the kids more mature in their learning in a way that doesn't necessarily show up in the test scores, but that at least, sort of within the context of the causal model, is likely to capture a big part of the effect of the intervention.
So would it be reasonable for a good causal model to work across regimes? So you mentioned like COVID, crazy time, right? So if you built a model that was stable, that got to the bottom of things economically or from a commercial perspective, for example, would you expect that model to continue to work even though things went crazy after COVID, if you think of COVID as an intervention of some sort?
Yeah, so I mean, I think that's a very interesting question. So in economics, in some sense, we've always been interested in causal models. And things have gone back and forth between building big models that were general purpose and that would allow us to answer lots and lots of different questions. But I was an undergraduate in the Netherlands, in Rotterdam. We had this machine at the university there called the Moniac. And that was a mechanical model of the economy. It was kind of a thing with a bunch of containers and pipes, and you would run water through it, and that would simulate the economy. And so you could do policy interventions there. You could have a government stimulus program, and that would be turning a spigot, and there would be water flowing in somewhere, and then you could see what that would do to GDP and what that would do to income and stuff. And so, but there were lots of questions you could ask that model. You could also ask, what would happen if we had fixed exchange rates versus flexible exchange rates that would be opening a particular channel? Or you could lower the interest rates. So you could answer all these different questions within that same model. Because that partly means it wouldn't answer any of these questions very well. By the time I was a student there, the machine was a little old and it was a little had some leaks, and so the whole economy would collapse very quickly after whatever the intervention was. But that type of modeling also went somewhat out of fashion in economics, because people felt these really big models were just too unwieldy to answer a lot of questions. And kind of when I got into the profession and the work I did with Angrist and the work that David Card was involved in, that Josh referred to as the credibility revolution, kind of was partly pushed back against that. And we tried to build much smaller models that really answered more narrow questions, but answered them well. And so this goes a little bit of a balance. And you see some of the academic literature goes in different directions. The directed acyclical graph literature has gone more in the direction of building these bigger models, where in economics people are still somewhat skeptical that in social sciences it's very challenging to build big models that capture lots of different effects very well. And so we often focus on more narrow questions, but try to get clear answers to those questions. Because both are very valuable, and there's sort of more and more work integrating these things. And in some sense, what I'm doing here, kind of with combining these experiments and the observational studies, is sort of partly going further in the direction of making more modeling assumptions, but doing it in a way that I'm still comfortable that the answers are credible, and there's a big emphasis on validating these models to make sure that I would be willing to actually bet on these models improving decision makings and giving better answers.
Thank you.
Great. Are there any other questions coming from online or in person? All right. With that, then, can we give another warm round of applause to Professor Imbens? Thank you very much. Excellent. Well, that's been a very strong start to the morning. I hope everybody agrees that these talks so far have been great, and I hope that's a good sign of things to come. We're going to be taking a scheduled break right now, so everybody can stretch their legs, get some coffee, get some food, and we're going to reconvene here at about 1:15. So thank you very much, and enjoy the break. All right, thank you very much. I hope that everybody had a nice relaxing break and has got their caffeine back in their system so that we can crack into the next session here. I'm pleased to introduce our next speaker here. She is a managing director at Scotiabank and has worked at such institutions in the past as Goldman Sachs, Citadel, and Morgan Stanley. She's here to speak to us about an intraday news event study and comparing and contrasting traditional and causal inference methods. So please, let's give a warm welcome to Judith Gu. Thank you very much.
Good morning and welcome to this session. I'm going to leave my cheat sheet right here, and hopefully I never have to grab it. So today I'm going to go over the causal inference methodologies in intraday equities market making. And I'm going to compare the traditional methods such as group comparisons using t-tests to the more recently developed causal inference methods like synthetic control, synthetic intervention, and causal impact. So here's our brief agenda for the next 20 minutes. We're going to go over a little bit about what is market making and what is a core challenge in market making and the role of a real-time news event. We're going to start with the traditional group comparison methods in doing the t-test comparisons, comparing the group average between the control group and treat group to more focused recent causal inference methods applied to the same space. And the methods we're going to go over is a simple difference in differences, Google's causal impact, causal lens synthetic intervention, and then we're going to share the results and talk about future work. All right, so what exactly is market making? So market makers are liquidity providers. We match buyers and sellers. So in the quant trading space, we're systematically sending out automated bids and offers continuously during the trading hours. And those bids and offers, they land in our client's order management system, sometimes called OMS. So clients have those quotes and sites, and if they're interested in our quotes, they'll send us a matching order to match with our quotes. So for instance, we're bidding $10 million of IBM, and our clients want to sell $10 million of IBM. Their order will come in towards our system. We go through an automated matching process. If everything matched up, we'll fill their orders automatically. So at that point, the client will have $10 million cash. We'll have $10 million of IBM in our book. And we also have a continuous hedging processing running on the side. So when hedging processing is an optimizer, it sees, OK, I have $10 million of IBM on the book, so I'm going to hedge it fully. So easy peasy, right? Everything works out. So nothing can go wrong, right? So let's take a look. So what is market maker's nightmare? It's right there, the big crocodile straw. So what I just described, the whole process happened within milliseconds. But none of that is market maker's biggest challenge. Market maker's biggest challenge is actually the stock's idiosyncratic risk when the stock is in market maker's book. And those idiosyncratic risks came unannounced. So if you can see this chart, it's an energy stock. It was working pretty nicely, right, with its peers. And it has a nice correlation with the blue line. The blue line and the white line was going well. But as long as when it's in our book, the blue line and the white line goes diverged. It has a huge intraday, we call it idiosyncratic risk or dislocation. This is where the market risk happens to market makers. And if you can see, if we long the stock, which is the white line, and hedge it with a sector ETF, which is a blue line, we're probably losing on both sides. And the jaw can go even wider, can go completely negative correlation. And that's the jaw that's going to eat us market makers' life. So we have to handle that. Oh, sorry, one more thing. So where does the jaw come, right? Like just not so long ago, it was working well. Well, the reasons or the cause can come from a few different places. It may come from liquidity, instantaneous liquidity imbalance, like buy-sell imbalance. In this case, most likely there's a big seller on the stock. Or it can come from temporary technical, oversold or overbought. The stock can be overbought, maybe recently, and it's doing a mean reversion, so it's underperforming the sector. Or it can come from fundamental. And fundamentals are reflected in real-time news events, because news events are actually real-time fundamental updates. And the goal of this session is to quantify how real-time news sentiment events impact intraday stock return. Okay, now we can go to the next slide. So the first methodology I applied is this good old group comparison t-test methodology. And the stocks are grouped into different, by events and also by different buckets. So we have intraday single news, intraday multiple news, overnight single news, and overnight multiple news. Because news affects whether it happens intraday versus whether it happens overnight, they have different impact on a stock. And multiple news also have different impact from single news. We have 4 different buckets, and on the row-wise, we group them by different news events for the given day. And both parametric and non-parametric t-tests was applied. And the universe coverage was about 1,200 stocks from both US and Canada, and the time range was between 2017 and 2023, earlier this year, 2023. And from the high-level look of the results, they actually make sense. The results match with intuition. The bad events, like the events we expect to have a negative impact, such as downgrades, inside sellers, do have strong negative t-stats. And the good events, which is upgrades and inside buyers, they do show up as strong positive significant t-stats. So it makes sense, right? We feel good about our hypothesis that news have impact on stock returns, and there's something in it matches with our intuition. But there are 2 large hurdles of this t-test approach. So the first one is t-tests cannot provide unbiased intraday trading strategies, as they cannot capture or condition confounders in a very robust way. So what do we mean by confounders here? So if we go back to this, the test here, we do use access returns. So access returns is we conditioned upon the sector returns from the stock return. So we do condition something. We took out the sector's return from the stock return. But there are far more than just the sector returns happening in the stock market. It could be a risk-on, risk-off regime difference. It could have a sector rotational. It has a style rotation happening when all those news are happening. So a t-test there's no easy way to condition those confounders as covariates. That's one biggest problem. And therefore, we're not 100% certain that those impacts are indeed only coming from news. It could be something else. But the second large hurdle is it's very difficult to mimic time series framework in t-tests. It just doesn't provide a natural way to plug in time series in the framework. And time series is absolutely critical and essential for stock trading and stock management, risk management. So what do we need here? We need to model time series with a causality base. And we need to provide unbiased point-wise prediction. And we also need to have a very robust, clear way to separate the actual move versus counterfactual move pre-post intervention. We want to know what the stock was happening pre-event and what stock happens after event, and how do we assess that impact after the event. And for t-tests, it only met really half of the first requirement. And the causal inference methods, as we're going to see, they match the other 3, all 4 requirements. So here, enter the causal inference method. And how do we construct a causal inference, build up the model? There are a couple of steps. First, we choose as industrial group to focus on. One very important construction in the causal inference method is your treat group and your control group has to have a lot of similarities. So the first and the foundational cut is to choose all the stocks in the same sub-industry. So first we choose an industry group to focus on, and in my study case, I choose the Canadian gold mining sector. It has about 60 stocks. And the time frame I used for this study is from January 2022 to June of this year. And then we spent a lot of time defining the treatment group and control stocks. So the treatment group is simple to start with. It's the stocks that actually had events on that day. An event we focus on here is the target price downgrade. A target price downgrade is analysts issued a target price downgrade on a stock intraday. And so the treat group is the stocks that have the target price downgrade on that day, intraday, during trading hours. And the control group is all the rest of the stocks in the same Canadian gold mining that has no news on that day. Not just they don't have target downgrade, but they have no other news either. But in addition to that, because we want to find we want to find the similarities as much as possible, we actually filtered on some additional variables, such as overnight return. Because overnight return has an impact on how the stock is going to behave intraday the next day. Overnight is from previous close to today's open. So we find the same, we only look for the same pattern with overnight group, overnight return in the control group with a treat group. So if the treat group has a positive overnight return, the control groups, all the stocks in the control groups all have positive overnight returns. And the other one we filter on is we have to ensure some minimum correlation for the returns pre-event between the control stocks and the treat stocks. With all those in place, we build a counterfactual time series, and then we estimate the impact. I'm going to go quickly to the appendix to show you what data frame we put into the model. Just let me go quickly here. There. So this is a test case we're going to go through for the causal inference methods. A stock called symbol AR had a price downgrade on March 7th at 11:43. And the control group it looks at is all the other stocks in the same sector that has no news and with the same overnight return pattern, as well as it has some correlation with the stock AR. And on the row-wise, it is by minute cumulative access returns. So every minute is its cumulative access returns for the stock from open to close. So there's 390 minutes in the trading day, and we actually have 391 data points. The first data point being the overnight return. All right, let's go back to the ones we're prepared. Oops. Oh, yeah, here we go. Validating results. Sorry, almost there. Yeah, right here. OK, so using that test case, this is a generic view of what the output looks like for causal inference methodologies. And you can see the vertical line is where the price downgrade happened around 11:43. And pre 11:43, that's the model fitting. It finds the weights from the control group to fit the actual returns of the treat group pre-event. And post-event, the dark line is the projection, or we call the counterfactual time series. The estimates about how the treat stock AR would have behaved had the downgrade did not happen on that day. And the gray line is its actual returns. And the difference is the causal impact, or the impact we want to look at. The gray area is the confidence interval. Next. So we tried 3 different causal inference methods. The first one is the great-grandfather of causal inference, a simple difference in differences. And the biggest upside of the difference in differences is its simplicity. We can manually quantify what the counterfactual data point is. But also the downside of differences is exactly the other side of the coin. It is too simple, and it may not be expressive enough to capture all the underlying behavior of the time series and its causality. And then we tried Bayesian-based causal impact. So the Google implementation was first pushed out by Kai Brodenson and the Google's team, and they have an implementation in R, use a Gibbs sampling. The time series modeling is a Bayesian time structure to catch the local trends, and if you have seasonalities, it can plug in that as well to catch more intricacy of the time series. And we can pass in non-stationary time series into the model without pre-processing the non-stationarity. So Google have the version in R, and then the version I tried here is from Python, which is implemented separately by Will Fuchs. And the model was implemented on top of a TensorFlow probability. And to fitting methodology was a variational inference and a Hamilton Monte Carlo. And then I also tried synthetic intervention. And this is implemented by our very own causal lens team here. And they use principal component regression to capture the model fitting from the control group to the treat group. And they also have a way to handle non-stationary time series. Yeah. All right. So high-level summary before we go into details is we found causal methods can infer significant negative impact on the price downgrade, at least for this test case we're seeing. And both causal impact and synthetic control methods give very similar results. However, cross-validation gave us mixed results, which we are going to talk about future work. So here's a result from a difference in differences. As you can see, we can capture the difference very easily, which is the difference between stock AR and its control basket before the intervention, the 0.1515 here, and then just shift this constant difference to the difference in the post-stock downgrade, which is 0.5386 here. And then we add them up. That became our counterfactual data, 0.6901. So it's very easy. You can even manually calculate. Although we can also go through simple ordinary least square to capture the coefficient on the interactive term. You get the same data. But it's very easy to understand, OK, you have a constant shift pre and post. All right. So Google causal impact, as you can see here, very identical charts as we saw before. Capture the fitting the model pre-intervention between the control basket and the treat stock. And then projecting the counterfactual move, which is a dark line you see. Which is the red dotted line you see over on top. So based on the counterfactual time series, the stock AR, if it had not, the price downgrade didn't happen to it, it would have moved drifting along the red dotted line. But with the price downgrade, the actual return is actually the black line. So you can see it implies a negative impact between for the event, given event, the negative impact between the red and the dark one. So the cumulative negative impact for the stock, since it received the event, is about 1.5 on the second chart. The third chart we can ignore because since we're using the cumulative rolling axis return to begin with. And then we can also get the different weights from the Google impact model. By the way, the difference in difference model, it has equal weights. So that's another limitation. OK, so here we have the causal lens synthetic control, synthetic intervention results. A very similar graph you saw before. We also have point-wise cumulative return here. And you can see at the bottom of the page, the cumulative impact is also around 1.5. So we have similar results here. All right, so we've gone through 3 models. The model fits the domain space. It fits, we can get some actionable items here. And so it works, right? We should just move into production. Well, not so fast. We have to do validation tests across the universe. And I ran the same model across the universe for the time series, for the time period we tested. And they actually, many of the test cases, many of the cases, they rendered very reasonable results, just like the results we saw. But we need to have like a statistical confidence that the model is actually going to perform well. So there are a couple of different validation tests that was recommended. In the original paper by Abadi in synthetic control, it mentioned permutation tests and robustness tests. So permutation test is like this. It's actually a placebo test on the control group. So we would iterate through the members in the control group and going through the same event. Well, the control group never had a price downgrade on that day. So that's why it's a placebo to the control group. But then we want to see how the model reacts for a placebo event. And the output for that test is something called post-pre-RMSE. So root mean square error. So we want to look at the root mean square error difference between post-placebo intervention to pre-placebo intervention. We assume they are going to stay alike. So if they stay identical, then the ratio will be fairly low, except for the stocks that actually went through the treatment. So causal lens model actually have such validation tests built into the model. It's on the top right corner here. So you can see that AR, which is our treat group, is the second highest post-pre-RMSE ratio. Another test is something called robustness check. Robustness check is to test, okay, what if I change my control group a little bit? Right, I'm taking one members out of the control group, one at a time, and just see if I still get the same counterfactual time series if I do that. And again, causal lens has a built-in robustness test right here on the lower right corner. The dotted black line is the one that we have every member in the control group. The gray lines are the ones we took one out through iterations. You can see the correlation is actually pretty high, except for 2 of them. So these 2 tests gave us a comfort. We think the baseline looks okay, but we want a more strict test. We want a true cross-validation test. And the cross-validation test we're doing here is taking all the time data point pre-price downgrade, and then we randomly creating placebo interventions for that time period. Because for that time period, the event didn't happen yet. And if we take those placebo tests, we were expecting the R-square in the test data will remain pretty high relative to the pre-R-square, pre-intervention R-square. And unfortunately, that's not what we found. We found mixed results. Sometimes the R-square looks good, but there's enough cases we need to dig into. The R-square doesn't look good. We expect them to look good because the event hasn't happened yet. And that's where we need future work. So hold that thought in your head for a bit. I will come back to that. But first, let me summarize the beginning purpose of this study, which is from traditional method to causal method. Again, hopefully it's a little bit clear to everyone now. The t-test is very good at defining the event impact on the very average statistics, but it lacks the confounding conditional mechanism, and also it doesn't have a time series framework built into it. The causal method has all of that. have all of their capabilities, and we can turn into something actionable for trading. However, at this stage, we still need more research into looking at why the cross-validation doesn't really work out as we hope it did. So some of the immediate action I can think of is, first, we can re-examine the control group. So even though the control group is from the same industrial sector, there might be other better ways to find similarity control groups. Because the industrial factor is defined by gigs, and which is defined by revenue streams to companies. So the companies sharing the most common revenue streams are in the same sector. But there might be other features that the companies may be the same. Such as in the gig study, folks found, okay, the Amazon is a consumer stock, or is a technology stock, or is it somewhere in between? So just strictly by defining by gig sector may not be the best way to define similarity group. The second one is we may want to look into, did the model overfit? I have an intuition that Google's impact model, because of the mechanism of variational inference and Monte Carlo, Hamilton Monte Carlo, it might overfit because just the way how those mechanism works. However, in a principal component regression model, the goal is actually not to overfit the model. So we have to look into what else is going on there. By the way, I missed one point in the synthetic intervention model built by Causal AI's team. They also testing two very significant assumptions. One is low rank, so the model doesn't overfit. The other one is causal transportability between pre-event to post-event. Okay, so as a bank, we're very practical, right? We look at bottom line all the time. So how should we understand this process? We do a lot of, we invest time in research, and we always have to show how it trickles down to bottom line. So I think we want to operate in the mindset of biotech companies or pharmaceutical companies that you always keep your pipeline running when you have something in production. So we want to keep pushing incremental actionables into production while keep researching in the pipeline, in the cutting edge front line in the research area, because research will show us something that we don't see in observational data, and it will lead us to opportunities and prevent us from the pitfalls. Thank you very much. I'm open for questions.
Great, thank you very much for that talk. I think we have time for a handful of questions here. So does anybody have any questions for Judith? We have one right here in the front.
Can you speak more about the similarity process? Is that out of the box that you were using for that? Was there like some slope matching process for determining whether they were similar for the control?
Sure, absolutely. So the first cut is all those stocks have to come from the same industry group. So they're all gold mining stocks. And the second cut is I look at because it's intraday, so the time spent is short enough to hold an assumption that those stocks will behave the same if nothing else happened. And so, but the second filter is overnight return, because overnight return have an impact on intraday behavior. And if a big positive overnight return, because of the sources how overnight return comes about. Overnight trading usually have very thin liquidity, so small trade will move the price in a big way. And those big returns, overnight returns, usually get reverted the next day when the liquidity is there. So we find the same overnight return patterns in the control group. So if the treat stock has positive overnight return, all the stocks in the control group, they all have positive overnight return. And also I made an optional parameter, but I do impose the minimum correlation between the treat stock and the control group before the event happened. And my threshold correlation cutoff is 40% at the moment. Thanks.
Great. Well, it seems like that's all for the questions right now. Oh, wait, we do have one last question here from over here on the left-hand side.
So for your future research, you talked about improving the method for finding the control group, or defining the control group better, right? What about the impact, the causal impact intraday, and what is actually creating the deviation from the control group? Is that important to you guys? And then how would you go about trying to calibrate that better? Because that's a problem with both the causal methods. They aren't quite getting you there, right? So.
Yeah, so you're asking how do we use it, right? Why do we care, right? So the way we can use it is assessing the impact of those events, because not all events have the same impact. And based on those assessments, so we can modulate our couple of different places. One is our bid offer quotes. We can either make adjustments there to make it less risky for our positions. And also, we can manage in the existing positions on the book. If we are long something and we just had a price downgrade, and we can figure out, okay, shall we actually take out the risk more quickly than usual, or how long it's going to last? How much the impact, it really matters for the remaining of the day. Because our study horizon is only from when the event happened to the end of the day. So we're assessing how much impact we're going to have for the remaining of the day. If it's going to have just for a huge negative impact for a few hours, and the next few hours it actually revert, then we're not that worried. We're not that nervous, right? We can let it flow. But if it goes all the way down towards the end of the day, then we may have to do something. We may want to do something there. Yeah, thanks.
Great, thank you. Let's thank Judith again for that very great presentation.
Thanks, everyone. Okay.
Thank you very much.
Okay, thank you.
All right. Moving right along then. Our next speaker comes to us from the Bosch Center for Artificial Intelligence, where he is a research scientist. He earned his doctorate from the University of Stuttgart. And yeah, we're very excited to have him here for his talk on the uphill battle for true impact in a diverse engineering enterprise. Let's give a warm welcome to Dr. Karim Saeed Barsim. Your weapon, sir.
Thank you. Okay. Hi, everyone. Of course, there isn't much space to add some value after the great talks this morning, but I will try my best. It's indeed a good opportunity to have this exchange and to exchange our thoughts and insights about causal inference with the community. And the title I promised the audience today, it's not showing up yet. Yep. The uphill battle for true impact of causal inference in a diverse engineering enterprise. And if you haven't yet noticed, by a diverse engineering enterprise, I mean something that looks like a Bosch. And I'm not from the marketing department. I'm actually a research scientist. And I'm, in fact, one member of an awesome research team there who shared a passion about causal inference and wanted to bring this to Bosch research and eventually to use cases in Bosch business units, simply because we envisioned a great impact of using that reasoning capability in Bosch use cases. But the question is, first, why? And a simple answer is manufacturing. If you didn't know, Bosch is a manufacturing-heavy company. It has plants all over the world, in different continents, in different countries. Many of them are in Germany, but some in the UK, in the US, China, Turkey, Australia, just what comes to mind. And these plants, not only do they produce with high annual yield, but also they produce safety-critical components. Take, for instance, the brake system in your vehicle, or the airbag system, or many other automotive components. They also produce healthcare products, for example, the COVID vivalytic test, or you may not know it more for consumer electronics and professional tools. On top of that, Bosch has a thing for innovation, for best-in-class, and most importantly, for quality. So after the end of line of a manufacturing pipeline, it has stringent quality assessment tests in order to release the parts manufactured to the field. If this is an environment where it relates too much to Bosch, how this relates to causality. And the answer here is that this environment is highly structural, highly modular, which is somehow linked to the main principles of causal inference, and independent causal mechanisms that don't interact or influence each other. And an acyclic graph is one common technique of modeling causal relationships. And if we look at how these environments are modeled, this should already trigger the causal reasoning lobe of your brain, and that's actually the main motivation that we started with. But this is one part of the answer. The second part will come in a few slides. Now for the agenda. For this talk, I will split it into 3 parts. The first is a review of the literature of causal reasoning and how it emerged into the machine learning literature. How we tried to identify some impact for Bosch use cases using causal inference, what impact did we target, and what impact we actually achieved. And finally, not to make this whole talk all about peace and beauty, just we talk about some technical content at the end. So research readiness. I guess this audience is already familiar with the remarkable growth of causal inference research that has emerged into the machine learning community. And I'm taking here a closer look at how it emerged into some of the top-tier conferences. I take 2 examples here, ICML 2020, and 2.5 years later, NeurIPS 2022. This is a point cloud that these conferences nowadays provide in their websites, where each point is a paper, and it's embedded in 2D space using some embedding technique, and they are rearranged based on some similarity measure based on the content of these papers. And highlighted in green are the causality papers submitted to ICML 2020. You can see already 2 patterns, one of them in the lower right corner, that causality has its own standalone cluster. It's the own problems that it's being addressed using machine learning, or in the machine learning literature. And it's also emerging as a complementary tool to existing machine learning paradigms. For example, causal aspects of reinforcement learning, or active learning, or probabilistic modeling of models, or data imputation, or something between adversarial and physical models. 2.5 years later, this thing doesn't change. It's still it's yet in a much larger number of papers. You see the clusters growing, and the complementary contributions are also much larger, maybe a little bit larger, but the same pattern still exists. A standalone cluster and another cluster another contribution that's complementary to other machine learning paradigms. Since this, this is off topic, but since this conference is 10 months ago, it's quite recent, it would be informative to have some quantification of the contribution of causal inference in these conferences. So this conference got 72 NeurIPS, 72 accepted submissions devoted to causal inference. 2 of them were nominated for Best Paper Award. 4 workshops dedicated fully or partially to causal inference and featuring keynote talks from Berl and Spirits. 1 competition and 1 dataset published for causal inference. Here is also, on the top right corner, the biggest cluster that this conference had, the reinforcement learning cluster, and you can see this, or you can, I highlighted that to have a feeling how large of the causal inference cluster compared to the largest cluster of that conference. Okay, that's achieved, and of course, from one keynote to the other in these machine learning conferences, you always see repeating appearance of causal inference. And in NeurIPS 2022, they questioned the validity of machine learning systems, and they just simply realized that prediction doesn't equal intervention, which is what we say in the causality, that correlation doesn't equal causation. And the same thing last week when I was at the AutoML 2023 conference, they just said feature selection in AutoML is just another way of causal discovery, or could benefit from it. Okay, for another audience, I would have gone through this mapping in detail, but for this audience, I guess you're more than familiar with this mapping. It's just a map that we used, a mental map that we use internally to pinpoint where would our contribution be. This is nothing but the ladder of causality, associational queries, interventional counterfactual, but top-down or upside down. And from left to right, the pipeline one follows when trying to build a cause or to answer a causal problem. First, collect the ground truth from the 3 levels that you might have: observational to address associational data, or experimental if you can, perform experiments, or finally the ground truth for counterfactual queries. We think of it as being the expert knowledge because this is the embedded knowledge and the imaginative process of humans. Then you put all this into a formal framework, causal models, and we highlighted a couple of them that has been so common in literature: the do calculus by Berle and derivatives thereof, for example, the signal calculus by his student, or the potential outcomes framework, and use that to answer different levels of queries. Okay, with that achieved, we can go to the next part of the talk, which is the true impact of causal inference that we wanted to achieve. And now comes the real battle, or the problem that we have faced in trying to achieve an impact in an engineering company like Bosch. Previously in the literature, I showed that there are 2 patterns of how causal inference emerged in the machine learning literature. One of them is a standalone, and other is a complementary. For many other industries that's not engineering-based, experiments are costly, are time-consuming, sometimes are non-ethical. But for an engineering company, we do experiments all the time. Our experts, our engineers, have built decades-long experience and know how to design experiments in the lab. And actually, the components, they undergo several experiments in the lab before they are even released. So having interventional data, experimental data, is so much cheaper than, say, social studies, for example. So we have AI or know-how that coexist together in such an environment, which could, of course, make good use of causal AI techniques, but we have neurosymbolic AI, for example, that combines the domain knowledge and machine learning. And if we talk about AI paradigms that try to use experimental data, there is a safe active learning or reinforcement learning. They have their policies to interact with the environment to collect interventional data on top of doing experiments as well. If we say, for example, causal AI can select relevant features to be explainable and to do some stuff that's reliable and stable, well, patient optimization and AutoML nowadays are doing stuff like this. They are not mostly related, or they are not focused all the time on predictive power, but also they are having some heuristics how to achieve this with some explainability in mind. Of course, they can benefit from causal AI, but this is complementary. And if we think about causal inference being stable and transferable and transportable to other domains because it learns stable mechanisms, well, there are AI paradigms such as transfer learning that take care of this or look into this issue. And it can benefit from causal AI, of course. But what are the unique problems that can be only solved using causal AI that hasn't been addressed using other techniques? And if we look at the previous map, we thought the unique thing that characterizes AI is being able to answer counterfactual queries. Because this is something that is not yet, I mean, at the time we built this, wasn't there yet, and it seemed to have no ground truth except just the imaginative power of humans. Maybe at that time we didn't have foundation models, maybe the discussion would have been different, but at least for that time, we thought causal AI is unique on doing counterfactual analysis. So this is where we thought the biggest impact of causal AI could be, trying to do counterfactual analysis with causal AI rather than answering associational queries or interventional. And this aligns perfectly with one of the most persistent and annoying problems we have in manufacturing, which is root cause analysis. In manufacturing, especially if you really care about quality like what Bosch does, then you may scrap a part after it has gone through a very lengthy and complicated and costly manufacturing process just because it didn't meet the quality criteria that, or quality standards that you have put. And this occurs, by the way, quite often. The manufacturing plants manufacture something like 200,000 pieces a day. Each one costs like, I don't know how much, but okay, some money. And if it's a continuous burn of money, if you keep just scrapping parts like this simply because you don't meet the quality criterion. And it's even more waste of money if you stop your production, guide your maintenance efforts to some stage which is not the root cause, and you can rerun the assembly line once again just to figure out that a couple of days later you get the same issue once again. So identifying the root cause that might lead to a cascade of failures, by the way, until it reaches the quality audit failure, is one important problem that we have daily on manufacturing pipelines. And it's addressed nowadays, or the state of art, using manual effort and lengthy RCA protocols. That's done whenever the human investigators, they have, or the engineers, they have enough capacity to work on the problem that's found in the assembly line. So it would be great alignment between the counterfactual capabilities that Causal AI provides and the persisting problem we have in manufacturing pipelines. So that's what we thought. Like, the true impact, or the biggest impact we can achieve, is doing counterfactual RCA using causal analysis. But that wasn't a great success, I have to say. The thing is, indeed, these environments are pretty structured, which is good for causality. And we could use the counterfactual reasoning from causal inference. That's good. But we faced so many challenges. One of them is that these models are quite complex. Like, okay, one step back. So causality, the ladder of causality is simply saying that causality is a cascade of ill-posed problems. You have data, finite number of samples, and many distributions that can fit this data. So you have to make some assumptions. You have to throw some assumptions to identify a unique distribution. And then many distributions, for one distribution, many DAGs, many causal graphs can fit that distribution. So you have to throw even more assumptions to get one DAG. And then many functional causal models that fit that DAG, so you have to throw even more assumptions. And by the time you are able to answer a counterfactual query, you have thrown so many assumptions that you can be questioned along this cascade of ill-posed problems anywhere. And counterfactual RCA is on top of that, on the peak of that pyramid of cascade of ill-posed problems. Add to that, once it reaches the top, it's to answer counterfactual queries using state of art, it's hugely computationally intensive. And for a huge graph that, I will show a graph in a minute, that shows up in a manufacturing pipeline, in a complex manufacturing pipeline with interacting root causes and so on, this doesn't scale. Add to that also that these environments are quite dynamic. They change over time. Each machine that keeps moving an arm 200,000 times a day to some position and gets back and to the same position again, keeps changing its initial conditions every time until at the end of the day you might get an error just because the state of the machine changes. And of course, in this manufacturing pipeline you have so many mixture heterogeneous mixture of data types that you should deal with. Starting from the IDs of the suppliers, the timestamps of a process, the numeric data types, of course, the categorical data types. So you have different data types, and all these are challenges that haven't been yet addressed from causality perspective. To give a feeling, we actually released one of the simple manufacturing processes. It's just a press fitting of some valves inside a pressurized chamber. And actually, this is released together with a library to synthesize some data from an imaginary assembly line that looks as complicated as this one. And you can see already how large scale that graph is, which is synthetic and is one of the smallest assembly lines that you can imagine. Now, trying to do root cause analysis on this, it's not an easy task. But along the way, when we tried to achieve that, we realized we have achieved another impact that we didn't envision at the beginning, which is simply putting a causal model. This is an example. This is just anonymous, some samples that don't make any sense for you right now, but actually putting our knowledge on the table together with the engineers so that we can discuss cause and effect relationships in an intuitive language was so much success. Because for a long time, when we as a machine learning experts, when we achieve or we celebrated so much the predictive power of our models, and even when we do like plus 5% above the state of art, we celebrate, but our end users, our engineers who would eventually use these models didn't share that excitement with us. They take these models with some happy faces, but at the end they don't deploy these models into real products because these are safety critical, they don't trust it, they don't know how to use them. But once causality got involved and we could agree on some principles or some intuition or some features to use, things started to change, and they started to take our models with some more confidence, maybe with a grain of salt. They didn't just blindly take the models, and we still have some arguments, but on the modeling part, not on the machine learning part anymore. But at least they started to build some confidence with these models, started to take them into action, to use them and give us some feedback, what to change, and how to deal with other aspects of machine learning. So the real impact we have achieved was not in the counterfactual part of causal analysis, was actually in the modeling part. And this gave us a language to deal with our end users of machine learning, which aligns, by the way, perfectly with the morning talks. Okay, so true impact, we envisioned counterfactual RCA, but we actually achieved structural causal modeling as a big impact for us. Now, for some technical part, say an appetizer for lunch. We did some work on causal discovery. Actually, we also did some work on counterfactual RCA, but I hoped it would be finished by the time, or it would be released by the time I'm here so that I can talk about it, but it will be released soon in 1 or 2 months. So hold tight for that. For the moment, I can only talk about a causal discovery algorithm. It's called VisAI, Variation-Based Cause Effect Identification. It's already published. And what it does is that it tries to figure the causal relationship between 2 variables in a system from pure observational data. It's up there in the top right corner. And the question we ask, if we had a distribution of samples from a bivariate system, only 2 variables, how can we tell if X causes Y or Y causes X? Those of you who know Pearl's work would know that CI tests won't apply in this scenario, but we have to use another principle. The principle that's commonly used in these situations is the independence of cause and mechanism. Cause is here, for example, X, and the effect is Y. And if these 2 mechanisms are independent, they don't interfere, they don't share information with each other, nor do they influence each other. And many techniques test for this postulate simply by measuring the mutual information between the 2 mechanisms in information theoretic sense, like colomographic complexities, but they are not computable, so they use proxies of that, like minimum descriptive length, and they check if these 2 mechanisms share any information. We take another approach where we actually test it by the same thing, the same principle we do with intervention, but now we call it variation because this is a more common term to use in probabilistic sense. So we introduce some variation in one of the mechanisms. Of course, this will be reflected in the final product, in the joint distribution between the 2 random variables, but we ask the question, do we also see it in the conditional? And if we see it, then these 2 mechanisms are not independent. If we don't see it, then it's more a relief that they could be independent. Let's keep this picture with us and jump ahead to the results. This is a result where we introduce more and more variations. So on the x-axis, we introduce more variations on the marginal of x. And on the y-axis, we quantify the influence of this introduced or injected variation on the conditional of y given x. And if you haven't figured it yet, this is the causal direction. This is sweet, nice, horizontal line that shows that no matter how much variation we introduce on the distribution of x, our conditional distributions don't change. While in the acausal direction, they keep just changing. Of course, it's noisy, but if we regress it, we just see a trend going always up in the acausal direction, while the trend is almost constant in the causal direction. This is a great indicator that we could use this technique for performing, for identifying the cause and effect in a bivariate system. Now, how do we treat it mathematically? I mentioned that we will introduce a variation so that we change one distribution from b of x to b of x with this lightning bolt. But this cannot be treated mathematically, so we introduce this quantifiable parameter alpha. And alpha is nothing but a reweighting of the samples. So to be honest, this b of x is nothing but a distribution you estimated from the samples that you got. And if you put some weights on the samples, so you change the weights of these samples, the importance of these samples, you get another distribution. This is nothing but the same technique that have been reused over and over again to balance some class imbalance data. Okay, so we put some weights on the samples, and we want some measure to quantify the divergence or the distance between these two distributions, b of x and b alpha of x. You have a bunch of discrepancy measures, KL divergence, Jensen-Shannon, total variation, a bunch of them, but we wanted something that is mathematically easier to treat. For example, to handle any data type, to be computable from a finite data set efficiently, and so on and so forth, to be symmetric. And one good choice for us was MMD, maximum mean discrepancy, which is symmetric, which is applied on a kernel, so you can just define a kernel on whatever data type that you have and quantify the discrepancy between the two distributions. Great. So how do we introduce a variation? We take this MMD and maximize it with respect to the variable parameter alpha. Of course, we need to make sure that this is a valid normalized weight vector, so we add a couple of constraints. And looking at the, sorry, one step back. So this is our optimization problem that gives us 1 point at the extreme of the graph. It just maximizes the MMD between the two distributions, gives us one maximum value at the end of the graph that I showed a couple of slides earlier. To regularize this, we just add one more scalar value, scalar parameter p alpha, that ranges between 0 and 1, and penalizes how much we can introduce of a variation. Looking at the estimator for MMD, you can see it has a quadratic form with respect to both the data types, the data, so it's a kernel, this K matrix diagram, the gram matrix, and of course it's also quadratic in terms of the alpha parameter that we want to maximize with respect to. So this already is close enough to a convex optimization problem, only that it's being maximized rather than minimized. We have a mathematical treatment for that, but at least for the moment, this is quadratic. These are all linear constraints, so you can use, so for example, CVX pi to solve this. And once you do that, you get a distribution of B alpha that looks like this. It puts all the weights in the outliers, so that it picks only the samples that are from, belong to the tail of the distribution and puts 0 weights on the bulk of the distribution, so that these two distributions are entirely different. With that, we have already introduced a variation. We need to quantify this on the conditionals. This is not as easy as the other one, but at least still we have a way to deal with it. I will skip it in favor of time. So these are the results that we have. They are competitive to existing state-of-art, not that superior to state-of-art, but at least we throw this result, this nice outcome as this one, as future work to explore this kind of technique for identifying cause and effect relationships, which actually concludes this technical part by introducing another mechanism to identify cause and effect relationships in a bivariate system. Now, this concludes my talk, but instead of having a summary, I would like to have one more slide, not to mention that I forgot LLMs. No, so they are there just to give you one of the perspectives that I have from causality side, which is similar to what happened 10 years ago. Like those of you who have been in the field of machine learning 10 years ago, I'm not that old, but I lived those days because it was the first year of my PhD. When this paper, AlexNet, came out, it showed an increase in performance of almost 10% beyond the latest algorithm that achieved the same, that was performed on ImageNet at that time. And it was received first with some skepticism, later on with some careful use, and eventually with wide adoption across various domains, deep learning. And nowadays, 10 years later, we have this paper that says causal reasoning and large language models opening a new frontier for causality. What they do is that they show that the Tupingen dataset, which is a challenging dataset for cause and effect identification, was challenging for many techniques of causal inference, with the best achieved 83%. Now, just asking ChatGPT to solve that problem achieves more than almost the same, so almost 12% increase in performance and detection accuracy. And it's still at the phase of skepticism, because even in that paper, they question whether or not this is a genuine result, or is it just ChatGPT memorizing the results of Tupingen dataset because it's open world, it's published. And I think we will soon enough move to the second and third phase, but for the moment, this is just a replay of the past. With that, many thanks for listening, and I conclude my talk.
Thank you. Thank you very much for that. Yeah, fascinating to hear how causality is applied to yet another industry over the course of this morning. So, are there any questions from the audience, both in person and online? We have one over from the right-hand side from Tom.
You mentioned that the causal modeling part was one of the big wins that you got. Was that because of the effect estimates, or purely from that communication piece that it gave you a shared language with the domain experts? And off the back of that, where do you see this going in the future in terms of building further in this use case and building on top that causal model?
So maybe the first option, so the communication or what, sorry?
So you mentioned that it helped you and the domain experts speak the same language. Were there other more quantifiable benefits of it in terms of treatment effects or predictive outputs and that sort of thing? And then where do you expect to take it in the future? So yes, it was mostly communication with the engineers, because we were not focused on treatment effects or quantifying the causal influence, even though these came along on trying to solve the problem of root cause analysis. But we had our eyes more focused on solving the problem of counterfactual RCA more than anything else. And eventually we found ourselves having these more confident discussions with the users of our models, way more than that we did before. For years, we have been BCI was there for 6 and 7 years now, and these models built or showed more hope in transferring the machine learning models to the eventual users way more than before. So the communication is the biggest win. Of course, there could be some other wins on the way, but we had our eyes more focused on the counterfactual RCA.
Great. One more question here in the center.
Thank you. I really enjoyed your talk. What was the P alpha function doing? I kind of lost it there.
Mm-hmm.
What was the purpose of that? What is the innovation in the paper that you had? Because I think varying both distributions and then checking the conditional is a standard idea.
Varying what, sorry?
Varying the marginal and then checking the conditional is a standard idea.
So the standard idea from literature is that one would, okay, let me jump to it. One would try to identify the mutual information between the two. So here K is a Kolmogorov complexity that shows how much of a complexity this distribution looks like, and if it shares some knowledge with the other distribution, the conditional, then this knowledge would be redundant, and one side of this inequality would be larger than the other. And of course, K is not a computable quantity, so the proxies thereof is, for example, S here, quanti-regression scores, they are doing regression and stuff, but again, they are proxies of colomograph complexities or minimum descriptive length. Trying to change one distribution and quantifying the effect on the other, I'm not talking about changing the variable itself, I'm talking about the mechanisms, so one level above, to change the mechanism itself and see if the other mechanism is changing, not to intervene on the random variable itself to see if I see an effect on the outcome. And this, I think we haven't found it in literature. If there is something like this, I would be happy to discuss offline.
That answers my question.
Sure.
Great. Are there any other questions? Well, with that then, let's thank our speaker one more time. Thank you very much.
Sure.
Thank you. Okay. Great. Well, it's been a great morning here so far. We've heard speakers, from the engineering sector, from the finance sector, from even the social policy sector. And I'm looking forward to hearing from our afternoon speakers to hear from a couple more applications in different industries. But before we hear from them, I think we've all earned our lunch right now. So we're going to be taking our lunch break. We're going to reconvene here in a little bit less than an hour or so, so at about 1:15 o'clock. So please enjoy yourselves, and for those online, try to grab a bite to eat as well. Thank you very much. All right. I hope that everybody had an enjoyable lunch. And yes, a big thank you to the facilities staff and the catering crew for all of the food and drink that they've been giving us so far today. Thank you very much to all of them. We are going to get started here with the afternoon's keynote speaker here. He is coming to join us from his role as the Global Head of Quantitative Research and Development at the Abu Dhabi Investment Authority. He also is the founding editor of the Journal of Financial Data Science, and at the same time, he's also a professor at the Cornell School of Engineering. He's here to give us a talk about causal factor investing, and he's asked me to also tell everyone that that is also the title of an upcoming monograph that's being printed by the Cambridge University Press, but which is currently available for free download. And I just tested this. If you Google causal factor investing, then you will find it as the very first link as the download. So, with all of that in mind, I'd like to extend a warm welcome to Marcos Lopez de Prado. Thank you very much.
All right. Thank you for coming. Thank you for inviting me. How many of you have heard about factor investing? So, pretty much everybody. So, as you know, factor investing is a very important part of the investment financial industry. Between $3 and $4 trillion are allocated to factor investing strategies. And those are strategies, those are vehicles that invest directly in factor investing. If we were to account for all the money that is invested indirectly in factor investing, it would be a multiple of that number. So it is by far the most popular investment approach. What if I were to tell you that this approach does not really have a solid scientific foundation? So I'll begin with the numbers. Can you show the slides? Good. Well, that's the performance of factor investing strategies going back to 2007. Why 2007? Well, it's when Goldman Sachs and Bloomberg began to track the performance of the most popular factors: value, momentum, quality, etc. And as you can see, it's a dismal performance. If you had invested in such fund, you would have made around 1% a year before transaction costs and management fees, with a very, very low Sharpe ratio, essentially doing nothing. So why is that? Remember, this is an investment approach that has been peer-reviewed to the infinity. There are literally thousands of papers published in the most high-ranking journals in finance supporting this. Why is it failing? Well, it is failing because it is based on very traditional statistical methods that were established back in the 1930s, what we might call the econometric canon. You buy a textbook at the bookshop, or you get it at the library. There are some very, very famous books of econometrics, and what you will find is approaches that are essentially associational. They have very little to do with what Professor Imbens presented this morning. And I celebrate, of course, that we have people of high intellect like Professor Imbens, who is changing the discipline. But the reality is that there is a battle for the soul of econometrics that is taking place today. Most financial econometricians are associational. Very, very few, Professor Imbens, one of them, is causal. And that's the difference. The difference is that these approaches just do not work. And remember, when we talk about $3–4 trillion invested in this, what we are talking is about pensions, savings. This is money that people actually need. This is not hedge fund money. This is money that many savers, retirees, are expecting to receive. They're expecting to get the return that was published in the journals, and that's not what they are getting. So what are we going to learn today? every student of statistics learns that correlation does not imply causation. Association is an observational property. Professor Imbens made the case brilliantly this morning, so I'm very happy that he already got us started there. Causation is an interventional concept. It involves an experiment, whether real or simulated. Now, causality plays a crucial role in the scientific method. Why? Because scientific theories are statements of the form X causes Y through mechanism M. Whenever you think of a scientific theory, it always boils down to this kind of a statement. You do not find scientists saying, well, when this thing and this thing happens together. That's not really how science works. Imagine a doctor who says, well, you know, when you take this, this happens. No, a doctor needs to understand the mechanism. Without an understanding of the mechanism, you don't really have control over what that supposedly medication or treatment is doing. But that's not what factor investing does. What they do, what authors publish in papers in financial journals typically do is they identify a correlation. You can express it in different ways. They run some regressions, compute some p-values, and they establish an anomaly, what is called an anomaly. But there is never a causal theory explaining why this anomaly occurs. So essentially, they stop at the correlation, at the associational statement. These papers do not make, or very rarely make, a causal statement. As a result of that, there are hundreds of claim factors that have been published. I just mentioned 4 of the most popular, but the reality is that there are hundreds of them. That's what has been called the factor zoo. And what does it mean, this factor zoo? Well, what it means is that you find all sorts of claims that are based on very short time series that may or may not have worked for the past 20 years or so. And the paper is published, and people put money on those papers. I will explain how we can differentiate between 2 types of flaw claims, false claims. One is type A spuriosity. Those are statistical flukes. And number 2, type B spuriosity, that's non-causal association. Let's begin with causality in factor investing. Why do we care about causality? Well, we care about causality because to make a prediction is not enough. I will make a clear example later on. Even if we were able to forecast, let's say, some prices based on some observed phenomena, that would not be enough to fulfill our fiduciary duty towards investors. Factor investing models, in fact, have some appearance of causality. A researcher typically will choose a particular model specification of this form, some variable y that they want to predict, let's say, the average cross-sectional returns, as a function of some variable x that they believe is the cause of that outcome, let's say value, momentum, and then they add some other regressors that they want to control for. They may want to control for, let's say, the business cycle, the size of the company, the economic regime. And when you look at this function, clearly, it's a causal statement. That's the most puzzling part of this story. It is as if researchers initially want to make a causal claim, but they never deliver the goods. They never present the causal graph associated with this regression. Why do I say that? Well, because they are regressing y, supposedly in effect, as a function of some causes. They are not trying to regress x as a function of y. This is not a distributional statement. It's not a statement that you would obtain, for instance, through PCA. You would obtain through a distribution of bivariates. No, this is actually a causal statement. Another way of looking at this as a causal statement is that they choose a very specific method, multivariate linear regression models estimated through ordinary least squares. Now, as you know from Econometrics 101, ordinary squares have some very interesting properties. For instance, they are non-orthogonal. They are non-orthogonal projections. So if we were to regress x as a function of y, we would not be able to obtain those coefficients based on the beta and gamma that we estimated here. There is a loss of information. Why? Because this is, in fact, a directional statement, x towards y. And as a result of that, there is some loss of information that would not occur, for instance, if you were to run an orthogonal regression. In addition, they also incorporate a number of causal assumptions when they run these regressors. For instance, they will apply y ordinary squares because they have the property that they are linear estimators with minimum bias. They are the maximum likelihood estimators with minimum bias. In fact, the minimum variance among the unbiased. So that's the Gauss-Markov theorem. Well, that means that they are actually trying to estimate betas in an unbiased way. This means that they are willing to give a lot of forecasting power in order to obtain an unbiased estimator. You see? This is not a forecasting model. In a forecasting model, you are willing to take bias in exchange for for minimizing the sum of squares. Right? That's what you would do, for instance, if you run a random forest regression. A random forest regression, there is no claim of biasness. Why are they applying an estimator that is unbiased? Because this is, in fact, a causal statement. They are trying to estimate beta in an unbiased way. So the question is, if this is truly a causal model, where is the causal graph? How do they know what variables they need to control for? They never declare the confounders. They never declare the mediators. They never declare the colliders. So how do we know that this is the correct specification? We do not know. In fact, what has happened is that they choose the specification that maximizes the R square. Not that maximizes the probability of obtaining an unbiased estimator. Right? They are not trying to impose a specification that allows for an unbiased estimator. No, they are trying to maximize the R square. So the conclusion is that there is a causal denial. On one hand, they use econometric methods that come really from biology, given the work that from the 1930s of Ronald Fisher and Carl Pearson and Nyman and many others, biostatisticians. But then they hide essentially the causal statements. They introduce some causal assumptions, but then they hide the causal statements. This leads to a state of confusion where on one hand, the model has all the characteristics of causality, but then they make associational claims. They are never providing a causal graph that can be falsified, that can be validated. What are the implications? There are two implications to this. Number one, that because they run so many regressions without controlling for multiple testing, the probability of a false positive rate is no longer a 5%. This is something that we know since the 1930s. Bonferroni is a name that probably you have heard of. Very quickly after Pearson and Neyman produced their hypothesis testing procedure framework, Bonferroni was the first one within months of saying, well, but this is only possible if you run the test once. The moment that you run the test twice, this significant level is no longer 5%. Well, Pearson's response was, of course, well, who would run this twice? I mean, it's so hard to get these estimates. Well, today, of course, we run millions and billions of regressions. And very few people in financial econometrics are controlling for multiple testing. As a result of that, even if the true value of the Sharpe ratio is 0, because they only publish the best performing model out of thousands, even millions of regressions, the expected value of the Sharpe ratio is increasing with the number of trials, even if the true Sharpe ratio is 0. And that's what is reflective of the first slide that I show you. Right? In the papers that you find in the Journal of Finance, Review of Financial Studies, Journal of Financial Economics, etc., there are claims of Sharpe ratios of 1, 2, 3. But then what you obtain is 0. Why? Because the true Sharpe ratio was 0, but they chose the best model out of thousands that they run. So they may claim a Sharpe ratio of 2, but the real Sharpe ratio is going to be 0. So this is type 1, type A, spuriosity. And the solution to this is well known. You can either apply methods to correct for p-hacking, like Hochber published in 1988, or you can publish methods to control for backtest overfitting, like David Bailey and I published in the year 2014. Then you also have type B spuriosity. What is type B spuriosity? Suppose that the signal is real. There is, in fact, an association. That doesn't mean that it's a causal association. It could be a non-causal association. Again, Professor Imbens explained this morning how one may observe association when there is no effect at all, which would be type A, but there could be association that is biased, that maybe there is no arrow between X and Y, and yet we will observe an association. And this is because the association flows through a backdoor. And this is the key difference between association and causation. We all hear the statement, association does not imply causation, but why is that? Why is that? Because causation is a very special type of association. Causation is the association that flows through causal paths. In this case, there is no causal path between X and Y. And yet, we will observe association between X and Y because it goes through the backdoor path. Why does association flow through backdoor path? Because it does not care about the direction of the arrows. Association is not a statement about X causes Y. It's a statement about two things move together. And it doesn't matter what moves first. Observationally, they move together. This is what we need to do. We need to control, in this case, for this confounder set. Now, some econometricians have made the claim, well, then what you can do is you can just add some variables, some control variables in your regression, as many as you can think of. And if they are a confounder, great. You will be able to block this backdoor path. And if they are not, well, they are not harmful. Wrong. They're, of course, very harmful. As we all know, if you control for a collider, you will experience, again, a false association, because a collider blocks the backdoor path. However, when you control for it, it opens it. So the solution is not just to control for whatever you can think of. You have to control for confounders. You need to have a causal graph that discriminates between confounders, mediators, and colliders. Only with knowledge of the causal graph you can propose the correct specification. Let me give you a couple of examples. Type B1 spuriosity. That's the spuriosity that occurs when you under control. There is a confounder. Let's say, in this case, you have a variable of the structure X causes Z, Z causes Y, X causes Y. Z, in this case, is a mediator. When you control for this mediator, you are estimating, you are blocking this path, but you leave this path open. You can do that, and you will be right if this is exactly what you wanted to estimate. However, if you wanted to estimate the total effect to control for a mediator, it's a very bad idea. Now, a more worrisome case is this one. Z is a confounder because it impacts Z, it affects Y, and then X causes Y. When you leave this uncontrolled, then there will be a bias estimation of beta. Let's look at the mystery of time-varying risk premia. This is something that has puzzled authors for decades, really. Why is it that factors sometimes work, sometimes do not work? The answer is when you have a confounder that is not controlled for, it could be that gamma changes and you are estimating a beta that will be very heavily biased. So the answer to the mystery of why there is risk premia that changes over time, why it's so unstable, is because researchers do not control for confounders. Now, let's think about type B2 spuriosity. That's the one that occurs for the opposite situation when you over-control. When you over-control, in this case, for instance, you're controlling for a mediator, in which case you are missing the total effect, or in this case, when you control for a collider. When you control for a collider, now you are opening this backdoor path, and beta will be biased. So this is a situation that is also very worrisome, because sometimes you fail because you didn't control, sometimes you fail because you control. You need to declare the causal graph. Whenever you read a paper in the factor investing literature or in econometrics in general, and someone proposes a specification, and there is no causal graph associated with that specification, most likely that specification is wrong. And as a result, there will be false positives and false negatives. So this is what is called Bergson's fallacy, when you control for a collider. Let's look at type B3 spuriosity. This is the result of a specification searching. When you look at standard econometrics textbooks, typically what they recommend is that you run a number of regressions and then you pick the best one in terms of explanatory power, in terms of greater R square, and so on. Well, when you do that, not only you are engaging in multiple testing, which would be the case of false positives that results from not controlling for growth in the false positive rate. But in addition, what happens is that now you are not making a decision on the specification based on a causal graph. You're deciding your specification based on associational estimates, essentially based on correlation. You are deciding your specification based on association, not on a causal statement. So that will, of course, lead to a number of false claims, too. Let me illustrate these examples with these cases, type B1, B2, and B3 spuriosity with Monte Carlo experiments. So the first structure is what is called a fork. A fork occurs when, well, you have a fork. Z is impacting X, is impacting Y. You run this regression, right? You run a regression where you don't control for Z, it's just the intercept and X, and you get here an R square, 25%, and you get a p-value of 0, essentially, because the t-value is 40 plus. So many researchers will stop here and say, OK, there is an association between X and Y. Well, of course it's not. There is none. This is a Monte Carlo experiment. I have chosen the data generating process. I know for a fact that there is no effect between X and Y. Why is the regression telling us that there is an association between X and Y? Well, because the backdoor path is open. The solution is to control for Z, and then we will get an R squared that is better, around 50%, and we will see that the p-value for Z is essentially 0, and the p-value for x is very high. So you could tell me, well, Marcus, that proves the point that doing this specification searching is a good idea, because eventually you will find a confounder, introduce it in your model, and you will obtain an unbiased estimate. Well, here we got lucky, but what when we use a different structure, what is called an immorality? Whoever came up with these names, but you know. This is the case where x impacts z, y impacts z, but these two, there is no arrow between the two. Okay, you run your regression, and what you obtain is a p-value of 0 for x, of 0 for z, which is a collider, but now we have introduced it as a control, and now you have an R² of 50%. Now the researcher might be very happy, because in fact, when we remove z, the R² drops to essentially 0. So if you are using a specification searching algorithm, now you will obtain a false result. This is false. And look, this is a very simple structure. Of course, there are colliders all over the place in the economy. The moment that you introduce in your regression, the result is completely biased. Now, let's look at the third case, a chain. This is a more interesting structure, a little bit more complex, but very common in investing, in finance. This is a case where Z is both a mediator, but is also a collider. You can see it here, right? A collider, but also a mediator. What do we do? What do we do in this case? Well, now, when you run the regression with this structure, so you want to control for x and z, you are controlling for this collider, which opens the backdoor path, and now there will be an association, but the association that you are measuring is not 2 or 1 and 2. It is 1, 3, 4, 5, is 1, 3, 4, is the backdoor path. That's what this regression is giving you. It's giving you something statistically significant, R² of essentially 80%, p-values essentially 0. A researcher will be extremely happy about this. We'll write the paper, type it, and send it to the Journal of Finance. Wrong. These estimates are completely biased. Now, when we do not control for z, now we have this path is blocked because this collider blocks 1, 3, 4. What remains open is 1, 2, which is what we wanted. And now there is a change in the sign of x. Here it is 1, here is minus 0.5. So not only the model that gives you the highest R² is the one that gives you wrong estimates, it's giving you even the wrong sign. You will do the opposite of what makes money. You will systematically lose money because you will buy things that you should have sold. You will sell things that you should have bought. Now, the R² of the correct model is only 15%. It's not 80%, it's only 15%, which means that using a standard econometric procedures, the researcher will lead us to a model that loses money systematically. And look, this is a very simple structure. Causal structures in finance are way more complicated. I could put here a model, a causal graph with 20 variables, with all sorts of connections, and unless you have a causal graph, you have no idea what the specification of the regression model should be. Now, think about this. We have hundreds of thousands of professors publishing papers that they need in order to get tenure, which of course they should. They need to publish, they need to make discoveries. But none of these papers, essentially none of these papers, propose a causal graph. So whenever they confront something like this, they will go for whatever gets them published. And then some investment firm will take this paper, package it into product, and it goes into your 401k. So what do we do? This is an amazing plot. This is the plot of the performance of all ETFs, all of them. All ETFs, factor ETFs. And this is the performance of the backtest, essentially the performance that went into the paper. This is from the moment that the firm took the paper and filed it with the SEC to apply for permission to market this. Performance is already flat, and this is the day that the fund begins to be marketed. You can now trade it. And you can see that it is not that the performance is ascending until here and then it flattens, in which case you could say, well, you know, maybe the opportunity is not big enough, so all the alpha has been arbitraged away. No, no. The performance flattens the moment that the application for the permission, essentially the moment that the model has been fixed. The moment that the model has been fixed, therefore, all of this is out of sample performance. This points to backtest overfitting. There is massive backtest overfitting taking place. Now, when you look at the most important papers in the literature, these are the Nobel Prize winning papers, like Fama and French, etc. These papers were written at the moment that, to be fair, these tools were not well developed. Perhaps they were known by some researchers, statisticians, but they were not well understood in our community. So, to be fair, they did what was common practice at the time. Now, of course, we know better. What is it that we need to do? Well, we need to identify what are the causal graphs involved in a regression before we choose the specification. Once we know what we are controlling for, of course, the causal graph can be wrong, but at least our statement, our assumptions are transparent to everybody. And now people can challenge our causal graph, modify it, introduce their own assumptions, and run their model based on their priors. But that's not what is happening. Essentially, what people are doing is they engage in massive p-hacking. They run millions of regressions. Number two, they under control. Even in Fama and French 93 and in Carhart, they mention several variables that do not make it into the regression. Right? So they perhaps, Fama and French 93, they miss confounders, they mention momentum, they mention macro variables, and they don't put it in the model. No explanation as to why. In theory, it would be because they believe there are colliders, but nowhere it says that. Then we have the problem of over-controlling, as I said, which is even more worrisome, I would say, because there are plenty of colliders in finance. And then specification searching. So these are essentially the four cardinal sins, right? You have p-hacking, you have over-controlling, under-controlling, and specification searching. This is what is the reason, the cause behind this underperformance that we observe in the first slide. So, based on this, what I propose is that we establish a hierarchy of evidence in finance. Not all empirical studies are born equal. The reality is that sometimes the evidence is very strong, sometimes is very weak. It's anecdotal at best. On one hand, you have expert opinion. You know, some investment guru tells you, oh, I see in the future that this is going to happen. Well, look, this is not a very sophisticated estimate because everybody will have their own visions, right? This is anecdotal evidence. Then you have case studies. So, for instance, a broker report, an analysis from a bank that says, based on our understanding of how banking works, we believe that, I don't know, UBS is underbought and you should put in your portfolio. It's not really an empirical analysis. It's more of looking at some evidence, anecdotal evidence, and making a statement. I don't say that they don't have value. I'm just saying that they do not have scientific value, which is very different. Then you have econometric observational studies. So this is really the most important part of the financial literature. This is the factor zoo. It's definitely better than case studies. These people really, they actually run some statistics through their models, not the best statistics, perhaps not in the purest way, but there is definitely some care is taken into finding these correlations. It's still low rigor. Essentially what they are telling us is there is a correlation here. We don't know why, but you should invest in it. Wrong, right? There is a correlation here. It's something that deserves additional scrutiny. It's not something that you should invest in just because there is a correlation. Many people tell me, well, but as long as I'm able to predict things, why shouldn't I invest? Let's say that I don't understand why X and Y are correlated, but I know that X occurs before Y. I have observed X. Why shouldn't I invest in the outcome Y? I don't know what is the mechanism, but there is a very strong correlation. Isn't that enough? And the answer is, of course it's not enough. Because you don't know what is the lurking variable that is going to flip the switch and make the positive betas negatives, and therefore you're going to lose money non-stop. It's not enough to rely on strong correlations. You need to, at the very least, rely on simulated interventions. A simulated intervention is a study that relies on a causal graph that is hypothesized. Perhaps it has been discovered utilizing various algorithms, like PC algorithm. The causal graph is hypothesized, and is presented as an unproven claim. So the author is telling you, if you believe that this causal graph is correct, this is the right way of structuring your regression. And these are the right controls, these are the right estimates. Now, you may disagree with the causal graph, and that's fair, because two reasonable people may disagree on the assumptions and still understand, given these assumptions, which you may share or not, definitely the empirical analysis was done correctly. And that's a simulated intervention. In many cases, that's the best we can do in finance, but this is definitely much better than hiding a number of choices, causal choices in your regression, and then portraying a result as something that is going to generate profits. A little bit better is a natural experiment. In a natural experiment, what you do is you take advantage of nature randomizing some assignments of subjects to various groups, a control group and the group on which there is a treatment. And then you observe what is the effect. This can be done very often in finance because, as a matter of fact, randomicity is all around us. The moment that a number is released, the moment that there is an intervention by the government, the moment that there is a corporate action. So there are some random effects, some effects that occur at the random time that allow you to conduct some natural experiments. And then, of course, the best that you can hope for is a randomized control trial. This, in fact, not uncommon in finance. Banks do it all the time. They produce what is called algo wheels. An algo wheel is a kind of A/B testing where you receive an order, you randomize it, and depending on the number that comes out of the random generator, you're going to send it through one algorithm or another algorithm, and you're going to observe the difference. And these are, of course, a very successful method that is used routinely by the industry, not really by academia. So, in short, there is a hierarchy of evidence, and we need to be very aware whenever we hear a claim, whenever a financial product is offered to us, whenever a paper is published in a journal, that even if the journal is very reputable, let's say the Journal of Finance, it could very, very well low rigor statement. And perhaps the claim appears in a journal that is not very famous, that doesn't get you tenure, but it could be very, very rigorous. And I could give you endless examples of such papers that may end up in it could be a randomized controlled trial that ends up in not a very popular journal, perhaps a journal of trading or some journal of market microstructure. On the other hand, you will have many papers that end up in the top journals, and really what they have done is they have reported some correlations and make the statement that you should invest just based on the correlation. Let me finalize with an invitation. At Adia Lab, we have offered an award, $100,000, to the best paper in causal inference applied to investing. What we would like is to incentivize that researchers do things with proper statistical methods. And I hope that all of you will submit. We have already received quite a few papers. The deadline is end of the year. And I think that it could be a moment that is, could be a watershed moment for the industry when researchers finally begin to use the statistical techniques of the 21st century. Thank you very much.
Thank you very much for that. Man, what a very interesting talk. That was taking me back to the first time that I encountered factor investing and like the Fama-French framework, probably about 15 years ago. And something always kind of bothered me as I was reading about it back then, but I never really had a language to explain what it was that was irking me. Now I think I have an explanation for it, so thank you for that. Are there any questions?
Great talk. Thank you very much. Are you aware of any reputable is maybe not the right word, but investment and management firms other than your own that are rigorously and carefully exercising this sort of discipline in actually managing real money?
I am. In fact, as it relates to execution, many firms utilize proper causal techniques. They may call it A/B testing, but for some very specific uses, they do it. They do it right. Now, for other cases, there is really very little incentive. Why? Because a portfolio manager receives a free call option to invest some assets. So there is a competition between portfolio managers to receive funds, and they tend to inflate results in order to receive allocations. So the industry is set up in a way that, in fact, disincentivizes the use of proper statistical techniques. That is not the case at institutions that are not structured in a performance fee model. For instance, sovereign wealth funds. We are expected to deliver performance for a country over the long term. So it's not about achieving a particular number this year. It needs to be over long periods of time. So the structure of these organizations does not really incentivize inflating results. You want to have the right results because you need to deliver this performance over long periods of time. But you're making the right point, and it's, in fact, the industry does not encourage the use of proper statistical techniques, hence the initiative of declaring this award. Yes?
Thanks for the talk. So I come from the world of biology where there's like more constrained laws of physics. Whereas like in the field of finance, you have like a positivity violation every single day because like market behavior is not constrained as much as human biology, and it will move faster. So how do you recognize when you're in a zero evidence positivity violation environment versus when you're not?
Yes, so that's a great question. Finance differs from biology and other experimental sciences in a number of ways. Number one, we cannot conduct experiments, control experiments in many cases. That's why we need to simulate interventions. That's why we need to apply natural experiments. So that's reason number one. Number two, our variables are typically fail tests of invariance. So they are non-stationary variables. There are changes in regulations. There are interventions by governments. Also, there is a very strict competition. That's number three. Very strict competition between market participants that it always brings the alpha down. Because in order to make $1, someone has to lose $1. And as a result, if someone constantly loses $1, eventually that person will disappear and the opportunity disappears. So it's a very competitive world where opportunities typically do not last very long. As a result, what is it that we can do? Well, what we can do is we can at least state our claims correctly. We need to state our assumptions and then let people challenge those assumptions. Perhaps these variables are going to experience a structural break as predetermined by the causal graph. Let me give you an example. The flash crash of May 6, 2010. So around noon, the S&P is down around 4%. It has been drifting very, very slowly. Market makers are struggling because they see a very highly correlated, negatively imbalanced order flow. So they're struggling, but they're still in the market. Eventually, the market runs out of market makers, and the price plunges within a couple of seconds, something like 6%, and then it begins to bounce back up. Now, many, many market makers went out of business that day because they developed models based on associations. This had never happened before. Therefore, models that based on associations, they are always backward looking. This association was not observed before. Therefore, they remained in the market providing liquidity until eventually they went bankrupt. However, market makers that rely on market microstructural models knew that they needed to monitor for negative order flow, toxic order flow. This is the order flow where you provide liquidity at your cost. You are being adversely selected. Those market makers that relied on a causal theory made a ton of money that day. Why? Because they knew that they had to get out of the market. You see, the theory predicted something that had never happened before. That's what good theories do, right? That's what the theory of relativity did. It predicted that if you wait for this solar eclipse, you're going to see how the sunlight is curved by the sun. It had never been observed before, but Einstein made this risky forecast, this risky proposition. And the fact that he predicted something that had never been observed before gave a lot of credibility to his theory. And today, we have performed extensive testing of the theory of relativity, and so far is holding up. Will we ever find? Of course, we will find one moment where there is some phenomenon that the theory of relativity cannot solve, but it is pretty good so far. The same happens with finance. Our theories do not need to be perfect. They need to be complex enough to take into account potential black swans, so that when the black swan occurs, we don't get caught like on May 6, 2010.
Thank you very much for the talk, Marcos. You're also getting praise from the live stream, and a couple of questions. So first one is, what do you think of causal graphs in light of what Soros called reflexivity? That is the circular cause-effect relationship in financial markets. Thank you.
Sorry, what is the question?
What do you think of causal graphs in light of what Soros called reflexivity being the cause-effect circular relationship in financial markets?
What Soros called reflexivity?
Yes.
Reflexivity.
Reflexivity.
Okay. Well, I don't think it's a causal theory. Look, in science there are situations where a statement is made, and we call these statements laws, which of course sound very strong, right? The law of gravity, or Ohm's law. It sounds even stronger than a theory, right? When you are put between a law, which sounds almost like a commandment, versus a theory, which sounds something weak. But in science, it's the opposite. We give much more importance to a theory than to a law. Why? Because a law is an anomaly for which there is no explanation. When you think about it, Newton never explained why gravity existed. He just made the claim, well, you can measure the force of attraction between two bodies based on the product of their masses divided by the square of the distance. But that's not a theory, that's an observation, right? That's an association that he has made. The same with Ohm's law. These are associational statements. We call them laws because they work. They work always, but we don't really know why. It took 100 years until Ohm's law was explained by a proper atomic theory, and it took about 300 years, I guess, maybe a bit less, 250 years, until Einstein was able to explain why Newton's law, which was not perfect in some cases, it seemed to work. So reflexivity is, in my view, a law. It's not a theory, right? It's an observation that a very successful investor has made. And as such, what it should attract is scrutiny. Why does this thing occur? We need to understand why, but we should not stop at thinking, well, this seems to work, because guess what? Financial systems are much more dynamic than biological systems. Very quickly, things can turn the other way around. In order to prevent black swans, you need theories. Laws are not enough to prevent black swans.
Great, and perhaps one more question from online?
Yeah, thank you very much for that answer as well. The live stream asks, what are your thoughts about effect heterogeneity and external validation in the context of financial experiments? And are you aware of cases of combining observational and experimental data in the field?
Absolutely, absolutely. One of the best uses of simulated interventions that you can think of is you begin with some observations. Based on those observations, you derive a set of causal graphs that are compatible with that observation, right? The observations, because they are associational statements, they can never lead you to a very precise causal graph. Causal graphs incorporate non-statistical data, right? That's why causation is not equal to association. You need to have a framework, a theoretical framework that explains why this association occurs. So you need to work backwards. You begin with the observations. Given these observations, these are the potential causal graphs, and there could be hundreds. And now what you need to do is you need to start to challenge those causal graphs. You say, if causal graph number 1 is true, then I should observe this association when I control for that. You do it, you do that simulated observation, and half of the graphs fail. Okay, so now instead of 100, now we have 50. Now you design a different simulated observation, and by elimination, you end up with a smaller number of graphs. And then what you need to do is you again need to use non-statistical information to make a claim. We do know something about finance and economy. After all, this is not coming from Mars. This is based on human institutions. We have some ideas to why the markets operate in a particular way. So that means that we can narrow down the graphs that are compatible not only with the observations, but also with our understanding of the economy. I'm not saying that there is a particular rule book that you need to follow. I'm not saying that utilizing causal inference, everything will happen automatically. No, but at least it allows us to narrow down what are the possibilities. And very important, state all of our assumptions for everybody to criticize. So again, yes, there are many ways in which you can utilize, combine observational studies with simulated observations to derive causal graphs that are compatible with the evidence, and then that's the best understanding that we have as to how the financial system works. Thank you very much.
Great. Thank you very much. Another round of applause. Great. Thank you so much. Take the clicker. All right. I'm going to ask everybody to just avert their eyes for about 60 seconds. We're going to do a little bit of furniture rearranging in preparation for the fireside chat. So we'll be with everybody in about 60 seconds here. So thank you. You got that one? Okay, that was a short 60-second furniture rearranging here. So yes, we are ready for our next set of speakers here. So it's going to be a slightly different format for this next session. It's going to be a less structured, more of a fireside chat. So the two people who are joining this fireside chat are Amit Gandhi. He is a vice president and technical fellow at Airbnb, formerly the chief economist for Microsoft Azure, and he has been a professor at institutions like Wharton and the University of Wisconsin-Madison. He's being joined by Pedro Santana, who is an associate professor at Emory University. He is also a visiting academic for Amazon and formerly of Vanderbilt University. So the two of them will be up here and having a nice little chat about causal inference tools and applications in yet another industry, the tech industry. So a big warm round of applause to welcome our two speakers.
Thanks for the introduction. Thanks for having us.
Super cool.
It's a great pleasure to me to be here with you, chatting. The time that I started as an academic, you were transitioning to the industry. I also took that path. Now I'm back. And yeah, so I'm very happy to be here discussing some stuff with you.
Congrats on all your success as well.
Thank you.
Looking forward.
Yeah, so the structure that we have in mind here is going to be much more informal than the previous talks. Right? So it's going to be like the two of us chatting. And since both of us have been in academia, then in industry, I thought the first thing that is very interesting for me to discuss, to bring it up, it is about the differences of causal inference tools that we see in academia versus those we see in tech industry. And we have been here the whole day today, talking about causal graphs, selection, observables, econometrics, and so on and so forth. And in my experience in the last 2 years that I spent in tech, it is that, usually we always start from that word, right? So we always start having well, we have a theory, we have some data that we want to account for, and once we select the variables that we think is important, we're going to deploy some kind of selection on observables techniques, I don't know, matching if you are some old school, inverse probability weighting if you don't want to model the outcome of interest, or if you go to the more modern world, you're going to do some kind of double machine learning. And in my view, in the last year, I have been seeing this everywhere I go. On the other side, in academia, right, there seems to be a big discount on studies that focus, put a lot of emphasis on observational tools, kind of unconfounded selection observables. And I find that very, very interesting, right? So this is the first observation I would like to make. It is that, at least in tech, as a starting point, even though imperfect, very often we deploy tools that based on selection observables, ruling out unobserved confounders. And in academia, you don't see that at least as the first stage in economics, that happens so much.
Yeah,
right?
Yeah, no, totally agree. And I think it's really interesting when we think about causality in this conference. By the way, Darko, congratulations, this awesome event. And I was telling him earlier, I feel like I'm at a Hollywood premiere here, but it's a Causal AI conference. Look, we just heard finance, applications of causal reasoning to making financial decisions. Technology companies, very interesting parallels. I mean, tech companies are in the business of building products, right? So we're building technology, services, cloud infrastructure, and you know, at the core of it is this causal question, right? If we build X, what's going to happen to the business, right? What's the outcome on customers, on the product metrics, shareholders, complicated set of stakeholders. So, you know, first off, as Pedro mentioned, like, you know, causal questions are first order in tech firms. Other part, though, as Pedro mentioned, there's a ton of data. Like these companies are swimming in data. We have more data than we know how to ingest, how to process. And so, you know, academics, and I come from, you know, we both span these worlds. A lot of these methods, what our preceding talk even mentioned, you know, they were born in very data-poor environments. You know, it's sort of we observe a couple things. Most of it is in the unobservable. Most of it is in the error term in the regression. It's not really in the things that we actually observe and control. And, you know, I just think, you know, with technology companies, we have lots of X's. And so it makes a lot of sense. Yeah. What is the problem of causality? Is there's some spurious correlation. There's some unobservable. What is the best way to control for an unobservable? Make it observable. Like, you know, observe the thing, proxy for it, you know, matching, inverse probability weighting, sort of a whole host of techniques. And it just makes sense from an evolutionary perspective to kind of start with data, correlations. You want to see, can I trust these correlations? If you want to stress test them, start controlling for things. And I think tech firms, being much more practical, have to sort of think in those terms. That being said, I think there's a lot of value in thinking hard about unobservables, because even if you think you've observed all the X's and we have the right specification, we have the right DAG, thinking about what could be wrong with it, which is really where the academic mindset shines, really forces you to discipline how you think about the mechanism. I mean, you probably don't have it right. Very few people get it right. Why might it be wrong is sometimes just as interesting as why might it be right.
No, I agree 100%. Everything Amit is like, it's true. There is so much data, right? There is so much stuff going on. And I mean, even when you have a DAG, and so everything is observable, we have to match that kind of like, that. The DAG gives you the identification, right? So it gives you like what you should account for. But then like in practice, we have to map that information to actually estimating. So we have to bring like the causal theory into practice. And that's where I think like in the tech firms, like we are really willing to go to the next mile using causal AI, causal machine learning, to avoid making functional form, to kind of like bring this kind of like second wave of a kind of quote-unquote causal revolution.
And one thing even related to the preceding talk, tech firms, being tech savvy, you know, we love machine learning, right? Give us machine learning. We want to use technology and software, and there's a lot of computer scientists running around. Sorry, no offense to the computer scientists here. And you know, it's interesting because some of the even simpler things we just saw in the last talk, just multiple linear regression, basic stuff, few thoughtful control variables. It's still very much in the minority. I've seen just in data science and product decision-making communities. And so I think there's still a lot of low-hanging fruit to double machine learning. You know, it's a little bit of throw the kitchen sink, right?
Yes.
I've got thousands of variables. What do I do? You know, neural network. But can I carefully construct these factors, if you will, you know, these concepts? I think there's a lot of value to that as well, and it makes sense to do both, really.
Yeah, I agree, 100%, right? So I think like one of the reasons that of this kind of like dichotomy of the two words, it is like there is this kind of bias for action. We cannot just sit for the perfect study, because like they may not exist, and just waiting for new data, waiting for like what should be done, it is like the cost of waiting is too high. So I think like what is happening these days, like we are bringing the information to the table, we're stating our assumptions, like we feel like there is uncertainty here, we are jumping from A to B, and this is only holding these statements. So I think that also like this, because the objective function of the two words is different. That explains a bit of these tools.
Yeah, yeah.
But I mean, at the same time, there is this elephant in the room, right? Unobservables, right? So, I mean, I can give you all the data in the world. There's still a lot of stuff that we wish to account for that there are unobserved confounders. So, like, Ibanez gave the early talk on today, combining experimental data and observational data. And the name of the game that was over there is like, well, we have these unobserved confounders that we wish to account.
Yeah.
And that is also something that is very fascinating to see the differences between like industry applications and academia. I mean, I made a career in academia out of differences methods, and this is kind of like trying to push for like accounting for unobserved confounders that is time invariant somehow. Like, but that's not the only game in town. I mean, in academia, in economics discipline, that's kind of like the bread and butter for many empirical tools, right? So, I mean, there is a paper saying like out of like, I don't know, like more than 20% of NBR working papers mention differences. But when you go to the tech industry, we see that like there is a lot of emphasis, a lot of appetite for other methods that account for observed confounders. So Judith like also gave a talk today about synthetic controls, and that is something that is also like appearing more and more.
Yeah.
And the dichotomy here is like, well, in academia we see a lot of, in publications, a lot of differences. In tech we see a lot of synthetic control methodology. And the beauty of these tools is that they can account for unobserved confounders, but it's not magical, right? So there is a structure, and yeah.
No, I think, look, it's interesting. You know, academics, and I'm a recovering academic, are paid to be clever, to be smart, to be thoughtful about how they think about data, and difference, and those who don't know the technique, it's very simple technique. I mean, maybe you can ask Pedro about it later, but you know, it's the kind of looking for these experiments and data where the experiment itself has like elegance, right? It's beautiful. It's you can represent it in a picture. You could understand problems like what's the effect of minimum wage on the economy, and been some really, really beautiful papers written. And it's thoughtful analysis. But going to your point, you know, tech companies, you know, it's about speed, it's about practicality, it's about decision making, and there's just not a lot of time to meditate on. And so the beauty of these other techniques, like synthetic controls, it captures similar reasoning. A synthetic control is, I have an observational unit that received a treatment. I'm trying to create the same observational unit without the treatment. I don't exactly have that same observational unit without the treatment, so I can synthesize one, right? It's sort of very, very intuitive. Something data scientists can do, something teams can build, something that can be explained to executives. And so I think one thing interesting as you go from, and I think everyone has experienced this, as you go from academics to industry, the set of things that work well in academic seminars and the set of things that work well in organizational decision making, that intersecting set is almost like it's very small.
Yeah.
And those techniques are the killer techniques, and I think you know, distilling what those are, synthetic controls, I think in instrumental variables I tend to think is useful, regression. I mean, there's a lot of just basic stuff that's really helpful.
Oh yeah, I mean, I think like the key on this is to recognize and acknowledge that we live in a world that we cannot account for everything we want to.
Yeah.
I mean, like the Nobel Prize, like 2021, about instrumental variables, and that's the name of the game, right? We're looking for randomness in stuff, like what is manipulating, affecting along in the causal chain. Because, I mean, in this world, when there is selection, right? And, I mean, I have the data in my hands. The decision makers, the stakeholders are asking us for new insights. Should we keep doing this program? Should we expand the program, right? I mean, at the very early stage, you may say, well, there is too much pressing demand for us. So we say, well, what's the data that we have? Like, oh, we have this data. Oh, is it perfect answer? No. Can we account for this somehow, like unobserved confounders in one way? And I have been seeing like more and more of these techniques accounting for unobserved confounders, like being deployed at scale in real time in tech companies. That is like, it's one of the areas that I have seen that's like academic work and real life applications that are getting connected. right? So
I totally agree. I mean, it's one of the more exciting areas, and sometimes lots of buzz phrases, but heterogeneous treatment effects is one that you can reference. But I mean, when you think about using, let's say, causal measurement in a technology setting, I mean, I think there's two distinct use cases to bear in mind. One I will call online application. So literally you have an online system. It's able to causally assess what would happen if I present this customer with this marketing treatment. And it would segment, and it would apply levers, and it would create feedback loops, and that's a system, right? That these are systems that companies are trying to understand and build. Obviously, for that kind of a system, you want techniques that are simple, robust, scalable,
and transparent,
and manageable. I think for the other application, what I'll call offline application, is you're not in software, in real-time software, but you are doing offline assessments of your business, right? This is what data science teams do. This is what analytics teams do. And even there, looking at heterogeneity, why did the causal effect of something I did in the past differ by some segments, by some groups? The most basic segment would be the value of your customer, high-value customers versus low-value customers. So if you have like an A/B test, and you find that the lift is 10%, but the lift on your low-value customers was 20%, the lift on your high-value customers was minus 1%, do you still want to proceed with the action? I think those are the really interesting business conversations to have. Most executives don't care that much about the average treatment effect, right? You could say the lift is 5.
Yeah, I agree. So like that's very cool, because like even when you have a clean experimental data, you run your A/B test, everything is like super well designed, a lot of thought was processed. How I map that knowledge to decision making.
Yeah.
Right. So and that's where like observational causal inference tools has a huge say on that, because like, well, I have this experiment, I know my underlying assumptions are valid. Now I want to segment my user base or like my population into different like groups, and in that case, how do I do that? Yeah. Right? So I mean, is there a guided way? So can you use like causal trees, like forests? Can you do segmentation? And then these two words of experimental world and observational world get together, and this is actually like moving forward, and it's very exciting to see that happening.
Super, super exciting. And I unfortunately had to miss Guido's talk in the morning, but I mean, very much a frontier area. If you have the ability to run these A/B tests, like our previous speaker mentioned, and tech companies do, we can randomize treatments. We could randomize traffic to different experiences, but you still have to get insight from that. It's not just a number. I mean, blending an A/B test with like a time series, or blending an A/B test with some kind of like a structural economic model of your environment. I still find it remarkable, like our previous speaker mentioned, how few DAGs are written. we all know, sort of there's causal structure encoded in this language. It seems like an obvious opportunity inside organizations for data scientists to speak to business stakeholders and conceptualize the DAG. Right? There's an intuitive DAG we have in our minds, as opposed to doing it intuitively. We can do it formally now. It's 2023, and I think it's a huge opportunity area.
No, I love that idea, because for many years we have been doing like this. At least in economics, the world have divided, right? So we have like reduced form causal inference folks, we have structural folks, but I mean, at the end of the day, the end game is the same: is to add value, is to improve things, to make better decision. And at the moment, very often we do have a lot of information from subject-specific knowledge. And the next thing that we should be doing it, and we're seeing this happening more, is like talk to the people who know the systems, talk to the people who are experts on the subject, right? Impose this structure, like up to some extent, into your model, such that the causal model is, it's also mimicking the concrete application, so you can get signal, you can gain power, you can move faster, right? Because if you are like, people say, oh, causal inference is kind of like, it's structure agnostic. I usually say, very often you're not structure agnostic, because behind the scenes, when you move from identification to estimation, you're imposing structure behind the scenes, right? So what we should be doing is be more like structure aware instead of structure blind and get the best of the words, because at the end of the day, we are not in the faith business, right? So we have to like, this is reality. We have to be bringing like what we know to the table, like, and say, well, now like, this is reality. We can validate our models, move on, like adaptive experimentation to validate things and make better decisions.
Yeah, yeah. No, I mean, I think, yeah, like all fields have factions and wars. In economics, and the types of economics that's made its way into industry, there is sometimes called the reduced form versus structuralist view of data. What we saw, like in the finance talk just now, was often a reduced form view of economics, that we can boil the world down to a y variable and some x variables that impact the y variable. And the goal in that case is some kind of measurement, right? Measure the effect of x on y. I think there are other schools of thought that are not first and foremost focused on measurement per se, but modeling, like understanding a mechanism, understanding how a complex process works. I think someone referenced biology earlier. Lots of economists view economic systems as complex systems that can be modeled and can be understood. Businesses are highly economic. There's demand functions, there's cost functions, there's equilibria, there's game theory. Bringing all of that to bear on your causal theory of reality and using data to estimate those structures, it's a very, very different kind of practice than oftentimes what you see in industry, but I think another low-hanging fruit, I think, for the field.
Yeah, but I mean, this is the kind of our ideal world, but the real challenge is to bring all these innovations in a unified language and translate this to decision makers, stakeholders, right? So if you see like traditional stakeholders, they look at dashboards, raw data to make decisions, and it's still not clear how like we translate all these causal tools, right? All this causal information, all these counterfactual assessments. You bring this to a meeting and our stakeholders in a way that like they understand the language, we all on the table, they understand the notion of uncertainty that we're talking about. And I think that's like what we should also be moving forward. And it's a kind of an open challenge. This is kind of a call for everybody who is here, everybody who is joining us online, to kind of like think about how we can move this, create kind of causal inference community that everybody like leverage the information. To the end game is to make better decisions.
Yeah. No, and I think, we were discussing before, lots of good executives have a causal theory of reality in their heads. So what do they oftentimes want to see is it's data. Show me metrics, show me dashboards, show me OKR, show me this deluge of highly correlational data where the causal filtering is happening. Where? In a boardroom, in a meeting, in a discussion. I think the interesting challenge for this community is now that we have these tools, you don't have to do it intuitively. How do you start to reconcile that with really that very traditional mindset? So if you come out with, and we were joking before, if you have a causal model that goes in the opposite direction as the correlational model, you kind of have an uphill battle to climb in terms of convincing your decision maker that A is the way to go versus B. So I think we haven't figured that out yet, as far as I can tell.
No, I agree, and that's where like this coming up with a language. I mean, that is the whole path of like educational perspective as well, bringing these tools to the mainstream, right, making everybody familiar. And I mean, also there is like unobserved confounders.
Yeah.
And what I wish, because I mean, whenever you see this kind of sign flips, right, or like results going in different directions, you have to go and own it, right? And very often it's like, everybody has a backstory, or like kind of, oh, what if is this? What if is that? And often we don't have this kind of ways to quantify that in the data, because if this was feature that was in the data, we would have accounted for.
Yep.
So what I'm wishing moving forward is like we can do more sensitivity analysis type of work, right, to kind of like find a way to quantify how much like our conclusions it is actually being like guided through assumptions and how much it is not, right? So if I were to relax my assumptions, I don't know, like 5, 10, 20% in some way, would that flip my decision? And that would also help to make more robust like causal put causal inference at the forefront and making more decisions, more informed decisions.
Yeah, and that's one thing beautiful. I'll say the last thing, I know we're at time, is in a business setting, in a tech company setting, people don't expect you to have all the data. Like it's understood that the world isn't perfect and knowledge isn't perfect. So you're allowed to make assumptions, right? Assumptions are okay. It's like as long as you state it. And one great way to fill a gap in data is to make a reasonable assumption. And I think it's another highly underutilized opportunity for the field.
Yeah,
all good
with that.
Thank you very much to both of you with that. Definitely some of the items that you brought up there definitely resonated with some of my own experiences in this space. So I think that that's probably the same for a lot of the audience members here. So are there any questions for either of our panelists here?
Thanks. Well, thanks, Pedro and Amit. Really great fireside chat. So if we take learnings from the challenges that data science teams often had in making models explainable to the line of business in a correlation model, what can we take from that and learn from that specifically with how we bring causal models out to the same group of folks?
So I'll go first, then you complete.
Sure.
So what I have seen being done is like we compute this like black box model, right? But then it's like you have a customer comes, well, but why my metric is this instead of that? Right? So we have to find, we should like find a way to decompose the channels, the mechanisms, at least to summarize, to give a first order approximation of why we went from A to B, right? And what I have been seeing doing this is kind of decomposition of the overall effect into mechanisms, or like using kind of like causal trees, right? So you have a decision maker, so the path of the treatment is here. Also have an underlying, like if you want to use a DAG, so the intervention was made here, then you decompose how the changes affect the whole system. That usually requires additional structure, additional assumptions. Right? So that's where like the knowledge of the subject specific helps, because that's where I think is like to have this kind of mapped out. So a customer come, say, oh, I see this metric, where should I interfere? Right? So that's like having that kind of map out, it is the way to go.
Yeah. I mean, it's a great question. I'll tell you my little trick that I've used in a data science space, and maybe it'll apply to a causal space. It hit me like a ton of bricks at some point that, it's sort of about trust, right? This person's telling me something, or this model's telling me something. Do I trust this, right? And in academic world, we're really focused on the model, right? This beautiful structure, the DAG, the science. But in a business setting, I started to realize it's only me who cares this much about the model. Like, people around me, what do they see? They see the inputs, they see the outputs. And I think it's really important to just have that recognition that a lot of trust comes from trusting the inputs. Am I using the right inputs? Oftentimes in academics, we try to use less inputs because it's more parsimonious. It doesn't make sense in some business settings. It's just like, why would you do that? Like, why would you drop like a fundamental input that I care about? And then outputs, of course, it's really hard, right? I mean, you have to think about, it's not about tables. It could be sometimes. It really depends on the organizational setting. But I mean, certainly I think all of us are hip to this fact, like visualization is really powerful. And like, I think data viz is a really powerful field. And I think getting out of Excel line charts into something more cognitively real is still kind of an open question, I think, for the causal community. What does the output look like? But anyway, good question.
So I think it seems that we all agree that one of the big challenges is to bring causal instruments into the leadership meetings is to establish trust, like trust in this analysis. You just mentioned that we could try to do it via powerful visualization and really trying to explain, build a narrative around this. Besides this, how much do you think will also be relevant, potentially leveraging the quick iteration pace that exists in a tech company in terms of like, output literally per working day compared to, for example, academia, in terms of like, literally like, keep showing results and potentially, using this as a learning tool also for non-technical people to, slowly adapt and understand what causality means.
Yeah. I mean, look, I think it's huge. I mean, I think the ability to iterate means you don't have to be perfect. When to get going, to get some data, you can be a little bit more hypothesis driven. So it's obviously huge. I think how you iterate becomes kind of key. And are you iterating like in an organizational sense, like we're going off, trying something, collecting data, coming back, assessing what happened, refining what we're doing, or are we doing it in an automated way, which is like we're going to go to market with a class of models that we know are imperfect, but these models are going to learn over time and become better. I think both are really powerful. My own experience has been organizational iteration is not nearly as quick as one might hope or imagine. So I think kind of there's these notions of the build, measure, test cycles. I think it's what it's called, where we're supposed to go through these flywheels and get more intelligent over time. Really depends on the organization how well that happens. I think there's a lot of opportunity though in adaptive online iteration.
Yeah, I mean, I think like adaptive experimentation. If you're able to run an A/B test, like if we have that infrastructure ready, there's a lot of push for doing this adaptive experimentation. So you learn from the past, like combining reinforcement learning with experimentation in that sense. I mean, that's one area that I'd say has been pushed. But I mean, at the end of the day, it's true. So it's like, well, what if you're not able? What if you do not have that infrastructure, right? So I mean, I don't know, like some falsification tests, or like leveraging previous labs, right? To kind of like, well, or having very carefully defined guardrail metrics. That is, you should not suppose see like lifts where you should not sing. That is where usually I see how like we gain trust to like we are able to explain why we're getting what we're getting it. Yeah.
Great. I think we have time for one more question here in the front of the room. Oh, in the front, perhaps.
Thank you for the opportunity and thank you for the conversation. That's very insightful. I think you mentioned about the experience in academia and also the application in the industry. So I would like to hear if you have any experience about the transition from academia to industry. Like in academia, if we find something in the causal model, we can just report it. But in the industry, any result can immediately transfer into the cost and benefit. Like something that I might quite like at work, the first time the customer come to tell me that after launching this new product, I need 50 more new employees to support the service. Then I told them, my causal model said, we do not need that. So that's the first time. And the second time, because the treatment is not one time, we roll out the services state by state. So the customer come back, ask again, I need 30 more new employees, and I see the model doesn't support that again. Then the third time, customer come back and see, is your model accurate? I still see new increase in the demand. I want new employee. And probably this time, because the situation changed, I need to adjust my model, and my model probably still sees something different, but I worry that if I still shut them down, the customer may want to buy me a one-way ticket to the moon. So for this kind of situation, what would you handle, and how would you make the model? Like, is there any method we make our causal inference model not only deal with what happened before, but also have some be proactive, some more predictive power in the future?
No, that's a great question, and that's a very hard one to answer, right? Because, I mean, I think that really depends on the infrastructure and the structure of the company as well, right? So this is like going to be different places, like you have reacted differently. So it is true that like in academia, It's like, we're done, like, go home, write the paper, submit it, and then like, in economics, after 5 years, the paper gets published, right, or not, right? So, but in the industries, there is more interaction, right? So there is more pressure, right? So I mean, the customer is always there asking you questions, and depending on the rigidity of the company, right, there are different incentives, right? The first thing that I always think is like, well, how much do you actually trust the stability of your causal model, right? Because you train the model in one regime, right? I mean, we don't stop the clock, things are moving, and then the customer say, well, I should do this. And you say, no, you should not do it. You say, no, I'm going to do it anyway. Well, story of my life, right? So this happens a lot. So, but what we have to think about it in my way is like, well, does the regime change? Do we have the scientific evidence to still own our decisions, right? Because there is this dichotomy. Where does my job end? Does my job end on providing the scientific evidence and giving the advice and let the business decision maker call the shots? Or is my job actually to ensure they're going to like make my shot? That depends on where I am standing in the company, right? So I think it's very tricky. So Amit is much higher than I am.
We all struggle with this, but I think you'll always do better the more you own what you're building. So if you build a model and you want people to use it, I mean, you really have to try to own it. So to own it properly, my advice to you in that situation is you kind of have to define your own KPIs. Like, you built this model. How do you want it? Like, what does success look like? And we just heard before, it's not predictive accuracy. If you build the best causal model, it will by definition have less predictive accuracy than a forecasting model. And so I struggle with this. Like, what does success look like? And it could be some success in the data, it could be success in the business, it could be organizational success. So I think it's really being very proactive about how you want to be, not measured, but how do you want these ideas to get assessed in terms of the actual business? Yeah.
Great. Well, thank you again to Amit and Pedro. A big round of applause for them. All right, it is time for another break so everybody can stretch their legs out. We are going to reconvene here at the top of the hour. So go get yourself a beverage, enjoy yourselves, and we'll be back here in just a couple of minutes. Thank you. All right, we are going to be getting started here, so hopefully people can make their way in quietly. But in order to keep things on schedule here, I'm going to begin by introducing half of our next set of speakers. He is a professor of industrial engineering at Constructor University. So please give a warm welcome to Hendro Vichaksono.
Thank you, Michael, for the introduction. So, good afternoon, everyone. So today I am going to share with you about our research, ongoing research in different applications of causal AI in different industry. So it's also nice to be here with the causal AI community. So I'm from Constructor University in Bremen, in Germany. And today I will focus on some projects, ongoing projects that focus on the whole pipeline of causal AI and their application in several use cases in industry. So, first of all, I also would like to appreciate my team here. Also one of them, which also part of BMW research team, Ishant, will also join, also present his work. So basically, our background is not the computer science, but more like industrial engineering and management. So therefore, most of our research is driven by the problems in industry. For example, in supply chain, smart city, sustainability, energy management, and so on. So in terms of research spectra, actually we have just started to work on the causal AI for 1.5 years ago. Actually, we mostly dealt with knowledge representations, how to formalize knowledge into kind of knowledge graph, for example, and also conventional machine learning, and also explainable AI. Basically, we want to facilitate the decision making in the industrial systems that contains of just giving information, prediction, run some simulation, and then so that the action can be derived from this prediction and simulations. So what are the characteristics of complex industrial systems? So first of all, that in the complex industrial system, there are a lot of interconnectedness. Each of the components in the system are interconnected. So if there is one problem or one disruption, then it could propagate into or give a effect into different part of the system. For example, in the context of supply chain, so if you remember the accident of Ever Given, so that's a ship that stuck in the Suez Canal in 2021. So it caused some disruption in supply chain. For example, the container index price was rising because of the empty container and then some delays of the shipment and so on. So, and not just that the propagation of the effect goes everywhere, but the effect is also mostly non-linear. So that one small change can give huge impact in different fields. And again, so because of this, in the complex industrial system, that information flow is important. That means the information should be able to be consumed by the others, so it should be understandable, and also it should facilitate some kind of feedback loop so that the information that's come from one part can be interpreted by the other part, and also then some appropriate feedback can be given. Therefore, because of those characteristics in complex industrial systems, so a lot of requirements for the role of AI which should be fulfilled yeah, in this context. So if you see this, some keywords here, the light blue ones are actually the ones that could be fulfilled mostly with the conventional machine learning, like accuracy, that it can handle a lot of large amount of data, and also robustness. But not all of the AI system can fulfill the ones that highlighted in the dark blue here. For example, lack of transparency, and also explainability and interpretability. So, and also what's also already mentioned by this morning talk, Darko, said that also it should somehow consider ethic. For example, it's free for discriminations and so on. So the integration with existing system, for example, is not just that it can work technically, can be integrated technically in the system, but also can be accepted by human. So therefore, because human is part of the industrial system. So in today's talk, we will focus on 4 use cases. They are ongoing projects. First is about project management, how causal AI can be used to optimize the software project management in this case, and then how causal AI can help the policymaker in circular economy to increase the adoption of circular economy, and also to support the implementations of sustainable manufacturing. And at the end, Ishan will elaborate more on the supply chain management. So what the common approach that we follow is actually also aligned with the system like developed, is called DUI, so that we always first come up with the model, with the causal model. So the causal model here, we in one side we try to conduct some experiments using automatic causal discovery algorithm. And also, we also integrate a domain expert to validate that, or even like if the result is quite off, then the domain expert can model from scratch. And then we identify the possible causal effect and estimate the magnitude of the causality at the end to validate the robustness of the model. So for example, in software project management. So one, we focus here in the risk assessment, how we can optimize the project management, we can assess the risk. And first of all, we need to identify what are the key indicators that represent that can measure the risk of software project. For example, like complexity or quality that can be derived into kind of quantity, for example, line of codes and so on. And we need to identify what are the potential contributing factors that contribute or affect that indicator. And at the end, how project manager can use the result to mitigate proactively how to optimize the project. So you can see on the left side here a result of Lingam for the automatic discovery of the causal discovery, and on the right side you can see here like the expert or causal graph that modeled by the expert. So in this case is quite well aligned, so that like the commuter experience and the task type and so on, and soft complexity metrics like average cyclomatic complexity number can affect the risk of project. In this case, is measured by total number of line of code. So there's some differences, but we could say that it's aligned. So that means in this case, the automatic causal discovery can help to helping or assist the expert in generating the graph. But in some other case, it's different. So some of the algorithm, because of different assumptions, for example, that's made in the algorithm, for example, and also the data, it results in some graph that off from the experts. So in this case, therefore, this is important always to keep in mind that human should be in center of this whole process. So the result after doing the approach, this loop that I show you, so that, for example, the first finding is that the developer experience, or in this case, the committer experience, play important roles in reducing the complexity of the software. For example, it can reduce the number of lines of code up to 161 lines, and also the communication among developers can also lead to changes of the code after the post-main branch merge. So that means change after it's somehow finalized inside the team. So in this case, that means some derived action is that the project manager need to always include some people that is already experienced and also integrate some communication tools. So, and in the circular economy, we try to help policymakers in the European Union into developing some measure to increase the adoption of circular economy. Circular economy is the economy system that focuses on the reuse and recreating a product so that the product creation could be always continuous in like a loop. So to minimize the waste or to minimize the environmental impact. So in this case, with the similar approach, so in this case, we use the data from the World Bank and also from Eurostat. So here we found that this what do you call it? Circular material use rate is a good indicator to measure the adoption of circular economy on the macro level. So macro level, that means in the whole, on the country level. So, and we can identify here the different factors that influence the material use rate. For example, the waste collection coverage, compared to the waste that is not collected. So that means the percentage of the waste that is already collected, and also like the material flow. That means if a lot of material flowing in the system, in the supply chain, so that means its possibility to have more waste is higher. So you can see here some findings that we can get from the Causal AI, so if we increase the waste collection coverage by only 1%, it could result in substantial of increase of the circular material usage. That means the adoption of the material of the circular economy can be increased well. So therefore, some derived actions, like expanding the waste collection coverage, not only like the waste processing, but also in the collection, and also recycling, using more recycling materials should be encouraged. And the last, before I hand over to Ishan, is in product development. For example, in the development of a car, which features of the car can impact CO2 emissions. So we also use some data, still ongoing. So we want to use the data from the European Environment Agency combined with some company data. So for example, here we identify some of the causal factors that influence the CO2 emissions, like the engine power and also engine capacity and so on. So there you can see here that different factors give different effect to CO2 emissions. For example, here that is quite significant in increasing the CO2 emissions is to increasing the engine power by 1 kilowatt. That means, in this case, the product or automotive developer need to reduce the engine power. So, Ishant will go into detail in one of the use case, which is in supply chain management. So I would like to hand over to Ishant.
Just to round out that fourth use case then, to talk about the supply chain management, I'd like to introduce Ishant Gupta, who is a lead data scientist at BMW. So thank you very much, Ishant.
Yeah. So thanks a lot, Michael, and thanks a lot, Professor. So I think one thing we can collectively agree today is that if we had to make a drinking game today, it would be on the word trust. So we have heard this word a lot today, and I think I'll touch it once again. And I want to talk about few of the problems in supply chain. So I was talking during lunch with Mr. Puneet, also coming from the supply chain background. It's a crazy world right now in supply chain where we have a lot of problems, from semiconductor issue to the geopolitical issues of what's happening in the Eastern Europe, to our supply chains are more complex than ever, and the climate change, and all these issues are really big issues which needs addressing right away. So how we try to deal with this issue is usually we'll try to go the machine learning way, and that's where we'll have some really interesting conversations with the management. So I come from an entrepreneurship background where I know lack of money or less money is always a problem. And then when I moved to corporate, I realized that having a lot of money is always also a problem. So one of the biggest fear of the management always is that we'll end up spending €1 million on an algorithm or a tool, and in the end we'll just have an interesting number, a number which is not actionable, and that is where the problem lies. So during our conversations where we try to predict something as a data scientist, we go to the management and we'll explain our predictions. They will ask us that, okay, how did you predict this thing? And that's where these conversations start about the black box modeling. We'll start talking to them about post-hoc explainability methods like LIME and CHAP, and that's exactly we start losing them because they feel that we are not able to explain it well. There's lack of tribal knowledge in the models, and in the end it's just predictions. It's not a business recommendations which usually management wants. So talking about the use case that I worked in BMW and also with Professor Vikas Sono, which is also the current state of most of the supply chains where we don't have a lot of transparency about our suppliers, their state and their future state. So right now it will be more of a diagnostic analysis where it will be more reacting to situation rather than a proactive situation. And we won't know that how some of the external factors, like everybody knows that semiconductor issue is affecting the automotive, but do we know how much? Can we quantify the effect? Or can we know that how much maybe a flood can affect my particular supplier? And there's always this issue that we cannot simulate things. We cannot ask this what if counterfactual scenarios. So the ideal state always is that we would want to be ahead of the game. And that was our use case. And the heart of supply chain always is the suppliers. And what we wanted to do at BMW is that could we predict ahead of time which will be our worst suppliers, and not just predicting, but quantifying that, okay, how bad they will be, at what level, and then comes the counterfactual part that, okay, if there's a particular external factor in Miami, how my particular supplier is affected, and if I take a certain action, it could be that my material planners are involved, or my logistics quality specialists are involved, or my purchasing department is involved. What will be the effect then on the reduction of the backlogs of my suppliers, or in the reduction of the missing parts of my suppliers? So the approach that we took was, first we went to the experts. We wanted to gather their tribal knowledge, and that's where we utilized this multi-criteria decision-ship making method, specifically analytic hierarchy process, where we sat down with them, tried to identify the causal relationships, the causal methods, where we wanted to know that how external factors are affecting our supply chain and what are the rankings. And then we did the conventional way also, because particularly what I also wanted to do is do a comparison, that how maybe the traditional machine learning approaches are compared with the current method of escalating suppliers in BMW with the causal approach. So I wish I could show you our fancy dashboards, but it's right now in the stage of publishing. But what I can show you is this thing about the tribal knowledge graph, where we interviewed the experts and we got this beautiful tribal knowledge graph from as simple as how maybe a flu or an external event can affect our suppliers' backlogs, to something interesting like how a farmer harvest season can make us hiring of temporary workers, which could lead to some of the human errors and then eventually affecting my suppliers having the backlogs. So all this information we wanted to incorporate in our causal machine learning models. And not only that, what I was specifying is that we wanted to do this comparison, that can we compare what the experts feel about the current existing method of escalating suppliers versus the traditional machine learning methods with this causal AI methods. Now, first, I want to show you the transformation of where we were and now what capability we had. So before, we had little to no capability to simulate things, to know that how an external event is affecting our suppliers, or we were more of the reactive stage, not a proactive stage. But now we have this capability, and we can give this thing to the management that, okay, this is the supplier, it can go down maybe in the next 2 to 3 weeks. And if we take a certain action, potentially we can make sure that the supplier will be fine. So now coming to the results part, and the more interesting part is we interviewed the research again in a more research way, specifically again analytic hierarchy process, where we did this analysis on a interesting demographic of data scientists, business analysts, people coming from Spartanburg, US, to Brazil, to India. And the results were really interesting, where causal AI was preferred by all of the experts. Now you may think that maybe are we comparing apples to oranges, where we are comparing the current descriptive approach to predictive analytics to causal AI. And I think this is exactly what the point we wanted to show is the capability of causal AI. One of the more interesting stats here you see is that if we combine all the criteria from business accuracy to stress test capability and explanation capability, and the time to recover, the traditional approach of traditional machine learning approach of escalating suppliers with the current approach was more or less the same, which could imply that the experts, they don't trust the machine learning models a lot. And if you see the numbers between the explainability part, they really struggle. So I think I'll touch one more time the LLM part, which has again been touched a lot today. And potentially of how I see LLMs being utilized in supply chain is identifying those particular external factors. Something really fascinating for me was this tribal knowledge graph that we derived from the experts. And when I used to sit down with these experts, try to interview them, initially they used to say that maybe I don't have that much of knowledge, maybe I cannot give you much. But at the end of those interviews, we used to have a really beautiful diagonal cyclic graph. And that also applies that maybe instead of starting from scratch, we can use something like a LLM capability, And if you see what I got from just a few prompts, was really close to the ground truth. So it took me around 40 hours to interview the experts in order to get that tribal knowledge graph, but just with a few prompts, I got something that was really close to the ground truth. Then the other approach always is to use this causal discovery algorithm. So here you see one thing is the ground truth that we already had by interviewing experts, and then is by using different algorithms like resist or PC algorithms to know what they are recommending, that how the potential graph could look like. And now again comes the role of the experts, where they can come and testify. So in this particular graph, you see that the causal discovery algorithm is predicting that a missing part will cause a wrong delivery, whereas I think most of us can agree that it should always be the other way around, and that's again the part. Now, where also we can utilize it is at BMW, we do have this luxury of all these experts. How about companies which do not maybe have a lot of experts, or maybe small-sized companies? Because they are the ones who are more interested in this thing, that they'll always say that you have all these experts. In our case, we don't have these experts, and that's where we can utilize the capability of large language models and these causal algorithms to build more trust. And again, I want to stress on this point is that maybe the future of supply chain is just not better technology or more technology, but actually better trust. Lastly, maybe I just want to give a shout out to my team at BMW for helping us in this actionable path. Thanks a lot.
Oh, stay up here. Great. Thank you very much to both of our speakers. That's just so interesting to me about the sheer breadth of applications that causality has. I mean, we've heard about finance earlier today, but now we're getting to things like even software design and, heavy industries. Just so neat to see all these applications. Are there any questions for either of our two speakers? Yes. Right here in the middle, the microphone is coming.
Hi, thank you so much. Learned quite a bit. I was wondering, in scenarios like supply chain, where some of the conditions might be very variable and unpredictable as to what could happen. For example, nobody estimated COVID is going to happen. Nobody estimated that Ukraine-Russia war is going to happen, and then how things are going to pan out. So how does this help us be more resilient or robust going into future, where, let's say, an unseen or unthought of thing happens, and then it creates this chain of events that end up creating, mess. So how are these models more resilient to that, or how are we going to be handling those?
So maybe I'll just reframe your question. So basically you're asking about the black swan events, that how in those kind of scenarios. So again, a lot of things come related to trust part also. We saw, the supply chain was really damaged by these black swan events. So what we can do is that, yes, we can try to build those synthetic environments, maybe use different techniques, try to simulate the things. But I think that's where a role of a tribal expert becomes even more important, is they playing around with those scenarios, we giving them the capability of playing around with those scenarios, and then they are the ones who try to decide that whether it can be plausible or not. Talking also about the trust is that, yes, it won't always be perfect, but I think that's where I'll go the more philosophical way of what OpenAI CEO said, that that ChatGPT is not perfect, but so are we. So it's, again, the trust factor that we have to give it to the experts, where they play around with all these simulation capabilities, and then we see how it goes.
So perhaps I want to add something. So that means I think what Ishan's already mentioned is that the role of human here is very important. Even in the beginning of the process itself, Ishan's also mentioned that there is a lot of factors, possible factors, that somehow we need to, the factors could be like hundreds, even thousands. So we need to have the dialogue with the user or with people who are expert in the field. So that which factor that could be possibly are the influencing factors. So by using MCDM method like phagitopsis and so on, so we can kind of rank of these factors, and then see by using causal AI, we can then see the causalities, yeah, from these factors. So on the outcome, for example, like price or whatever what's the outcome is. Yeah.
Great. And I think I saw one more question over here along the right wall.
Yeah.
Thank you. Actually, I want to understand more about your use cases. Like you're working in supply chain domain right now. So like how do you actually operationalize your intelligence on the causal insights you got, and how do you solve the business problem on that?
Yeah, so I'll answer you how we do right now and also how we would like to do it in future. So right now what we do is that with all these insights, the final recommendation will be that who will be involved with dealing this kind of scenario, that it could be the purchasing department, it could be the logistics quality experts or the material planners, and we'll give them the intelligence that if the purchasing department is involved, potentially we'll see a reduction of, let's say, 20% of the backlogs of the suppliers. How I'll want to do it in future, and something that I'm working right now, is that to have this feedback loop with the suppliers itself. So we come to the suppliers, we tell them about these action points, and then take a feedback that if they took our suggestion, how effective it was and what they think of our suggestion. So that's how I'll like to want to go in the future.
Great. Maybe one more question here in the very front before we move on.
Sorry, just really fast. Very intriguing application of large language models there at the end. Could you just say a little bit more about how do you go from 40 hours of interviews to a few prompts with the large language model to construct the causal graph?
So basically what I'll repeat the question is that you are asking that it took me around 40 to 50 hours of interviewing the experts in order to get that tribal knowledge graph, and what could be the way of we can minimize that by using LLMs, right? So it's usually identifying those things, basic prompt engineering, and I mean, it's always better to give a initial overview that, okay, if we already have that, my missing parts will be related to the backlogs, and I want to know about some of the political issues, and I want to know about how the pandemic is affecting. Then it will come with a very general causal DAG graph. But then with prompt engineering, you can further ask that, can you tell me the more causal relationships that, okay, maybe a strike in Poland can lead my supplier backlogs to be affected. So it's just basic prompt engineering. And again, what was surprising for me is we think that these experts, they have a lot of knowledge, which they do, but it's not very unique in all the use cases. And what I got after just 3 prompts was very close to this ground truth. So what I am suggesting is an approach, instead of just starting from scratch with these experts, we can just use the LLM predictions or the causal discovery algorithms, and then the experts can further validate it or build onto that. You're welcome.
Great. I think another round of applause for both of our speakers here. Thank you very much. Here, I got it. Oh, okay. Great. So, for our next speaker, this takes me back way when I was a very, very junior data scientist back in the early days of my career. I remember I was given once a problem about doing predictive maintenance for rail cars. And I taught myself survival analysis and how to work with censored observations and so forth. And that problem, even though what I did was a very, very simple formulation, that problem's kind of stuck with me for the last 15 plus years. And it keeps on coming up in various contexts every once in a while. And well, it's happened again right here, because for the past 11 years, our next speaker has been working at Alstom, where he works as a senior senior data scientist working on, among other things, predictive railway maintenance. So, to speak to us about how to use causal inference for cracking that problem is our next speaker, Alexandra Tia. Thank you.
Okay, so good afternoon, everyone, and thank you, Causal AI, for having me. So, today, I'd like to talk about the maintainers, people whose job is to keep things working, put simply. And given that I'm in the business of railway transportation, the kind of maintainers I have in mind are the railway staff that make sure the trains operate reliably and safely, day after day, because this is important. On the one hand, we want trains to be reliable because we all commute and need to make it to the office on time. On the other hand, we want them to be safe for obvious reasons. Safety is of utmost importance in railways, for the passengers, for the employees, and for the public in general. Safety is a priority that must become before all others, and the risks must be minimized. So, in our causal inference context, what could be the effect of exposure to danger due to an unreliable or unsafe train? And you're probably thinking about accidents, right? So, this is Paris, 1985. The historically famous derailment on the Montparnasse station. So this particular steam engine had an issue with the air brake system that was available at the time, and as a result of this accident, there was one casualty and a partial destruction of the infrastructure. But the railway community learned from this catastrophic event, which spurred the development of more effective braking systems. So, fast forward 70 years. Modern trains, such as the ones we use today, equip what is known as a blended braking system, where two different braking technologies are smartly integrated. So, on the left-hand side of the slide, you see friction brake. In this setting, compressed air pushes the plunge of a piston, which moves the caliper, which squeezes the brake pads against the brake disc. And friction eventually transforms the kinetic energy of the train into heat. On the right-hand side of the slide, you see a schematic of a dynamic brake. In this setting, the traction motor is used as a generator. So the train in movement keeps spinning the rotor. The electrical resistance induces currents in the windings, which are then routed back to the grid for their reuse and into the rheostat, which dissipates the remaining energy as heat through the Joule effect. And this is all a bit of a mouthful, I know, but this braking technology is definitely more effective than the technology the steam engine had. So, here comes the question. Would the former steam engine have stopped in time had it equipped one of these blended braking systems? We can probably guess the answer to this counterfactual question. There's some missing information, that's true, but it's an interesting question nonetheless. The trade-off with this increase in effectiveness is an increase in the sophistication and complexity of the systems, which in turn make the job of maintainers increasingly more difficult. So in the middle picture, you see a brake control panel that's full of stuff. You need to know what you're looking for when troubleshooting one of these systems. And this is only half the story, as I'm excluding the traction unit. So, is this increase in effectiveness and complexity worth it? We're going to assume that it is, because nowadays we also have data. And with data come predictive systems that observe international standards, such as this one shown here, which provide guidelines to collect the data, process it, and provide the results in a way that the maintainers can make use of them in order to do their job more effectively. And with all these, we engineers can then come in and develop predictive maintenance solutions, which have to accomplish three main goals: the detection of anomalous behaviors, the diagnosis of the root causes, and the prognosis, which is the estimation of the remaining useful life, which is the time or the mileage left before the failure appears. So, does it make sense what I'm saying? The question now is data all we need to provide answers to these or to accomplish these three objectives? Nowadays, we have data collectors of all sorts. We have the GPS, we have the Internet of Things, we have powerful computers able to generate reams and reams of data. And trains are better today than they used to be in the past. But the world is changing constantly. And in this changing setting, it is reasonable to have some doubts. Will the extant technology perform well in this changing environment? Will that new technology developed in the lab perform well once we deploy it in the real world? And again, is data all we need to provide accurate, unbiased answers to these questions? I have some qualms about this, but it turns out that predictive technology is kind of limited in this sense. And we also have the causal technology, right? And causal inference is precisely the science that allows us to intervene in the world, change it, and evaluate the impact of these changes. So, we're probably on the good track if we adopt causality in this predictive environment. So, predictive causality, causal prediction, doesn't make sense to have these two concepts on the same page, because causal systems are not predictive systems. There's a fundamental difference regarding the way that they manage the dependencies among the variables that we use to model the world. Predictive systems are focused on mapping independent inputs to outputs and will do whatever it takes to adjust their set of parameters in order to minimize a classification or regression loss, oftentimes rendering them uninterpretable, which penalizes the confidence that we can give with the solutions that we developed. Alternatively, causal systems are focused on modeling these variable interactions, making it clear what's going on under the hood, and also possibly helping us deliver solutions with a greater degree of confidence. So, does it make sense to adopt causality in this predictive environment? My contention is that it makes perfect sense. And in this talk, I will try to build a convincing case for doing so. And to this end, I will borrow the well-known Simpson's paradox example, but instead of relating exercise to cholesterol, I'm going to put maintenance in the abscissa and cost in the ordinate. But the message that the graph conveys is exactly the same. Well, it may seem that the more maintenance you do, the more money you will spend. This is a deception introduced by the confounding effect of the age on your fleet. So, there may be different approaches to conduct the maintenance of the assets, and in fact, we have names for these. The kind of approaches that only fix the things that break are called corrective, and they're shown in red at the top. They are the ones that eventually spend the most. And then there are the schedule approaches shown in yellow. These approaches build maintenance plans at the beginning of a project based on some historical averages of degradation. And it's okay. They can reduce some of the cost, but up to a point, due to the overly conservative and risk-averse criteria of railway operation. And then there are the predictive approaches, shown in green. These approaches use sensors to collect data from the field, and they estimate the actual degradation conditions of the assets. And then they use this information to drive the maintenance actions in a more dynamic way. So these are the kind of approaches that enable us to explore new business cases, that comprise the observation of unexpected issues and that also allow us to exploit the full life of the components. Obviously, this is where we want to be with data science and causality. And in fact, the gist of these things I'm talking about is pretty well known to the maintainers, because engineers have been using them for ages under the guise of the failure mode, the mechanism, and the effect analysis, which is a set of documentation that describes the problems from the incipient point of failure until the system crash. And if we read these through the lens of causality, we are going to find the same fundamental underlying concepts, because we can liken failure mode to root causes, mechanisms to mediators, and effects to outcomes, therefore building a beautiful causal graph that we can exploit with the tools of inference. So, up to this point, I would say that we're in a pretty good position to justify the adoption of causality in a predictive environment. And to further convince you of this, I'm going to share with you two specific use cases that we developed at Alstom, where we leveraged that causal technology in a context of language and in a context of subsystem events, which are the kind of messages that flow in the backbone of the trains. So, to the first use case, the one that involves natural language or technical language, as this term better reflects the engineering lexicon and semantics of the return on experience records that we use for this research. So return on experience is a database, a written database, that describes the problems as they are found on the shop floor, and after the investigations, they also contain the information, they also describe their root causes and the solutions that were introduced to solve them. So it's interesting information for us to mine in order to provide further knowledge, this added value knowledge for the maintainers. So, while traditional NLP approaches would have tackled this setting using the localist representations with sparse vector spaces, we have here adopted a more modern approach using deep learning, so things like ChatGPT, that kind of stuff. So in this case, we're building distributed representations with dense vector spaces that already embed the causal information that we're interested in analyzing. So the point of this research is to develop causal word embeddings as a fundamental building block for other downstream tasks, such as root cause analysis. But obviously, these word embeddings are not like the traditional ones where you learn the local context of individual words. So these words for natural language, because that is governed by a context-dependent grammar. In this case, the causal information is found in the entailment of whole text. So our specific proposal for doing root cause analysis troubleshooting is to treat the whole text as a bag of words, model their entailment in the diagnosis direction, while conditioning on the context of the project to adjust for any confounding, which is what makes sense given the causal graph that describes the entailment in the text, which is shown up there in the top right-hand corner of the slide. So on the left, you see the neural encoding architecture that we use for learning this. We know from NLP research literature that we can peek into this learned representation by extracting the principal components of the embedding. That's what we're showing in the middle picture. And then by using a similarity metric, such as the cosine distance, we can then align the problem to their potential root causes and provide these one first step of added value knowledge for the maintainers. And finally, for verification purposes, we also conducted some sort of alignment analysis by taking into account the average probabilities from the model, taking also into account the fault tree that we derived from the FMEA documentation that I described previously. In this case, it turns out that if we get the wording that was used to describe the direct diagnosis and we compare it with the others, we found an overlap over 70%, which signals that what we are learning is meaningful and therefore it is valuable for the maintainer. So that was the first use case. The second one, the one that involves the subsystem events, which we here treat as binary variables that evolve in time. In this case, the goal of the research is to develop two modules, the one that detects the anomalies and the one that troubleshoots their root causes. And the interesting bit of this research, the capstone of the project, is the use of the variational autoencoder for implementing both modules. So autoencoders are probably the go-to solution for engineers dealing with an unsupervised environment, such as this one, where we only have data that comes from commercial surveys. And then this autoencoder model learns the pattern of normal behavior and then uses the reconstruction error to signal the presence of an anomaly. In this case, what makes the variational type of autoencoder especially interesting is the added regularity in the embedding, which then becomes a manifold, which is a locally Euclidean space. And then we can use it for generative purposes, which we exploit for doing interpolations and extrapolations, which is especially interesting in an environment where we don't have examples of failures. So on the left, you see the neural autoencoder architecture with a focus on the bottleneck, which is where the manifold is to be found. And in the middle picture, you see a representation of this manifold, where you can see how the normal data gets clustered at the center. Then, on this space, we can fit a smooth probabilistic function to signal the risk of an anomaly. And once we introduce a threshold to that function, we tessellate the space so that anything that falls out of this corral is logically regarded to be an anomaly. And obviously, once we spot an instance that is suspicious to contain an anomaly, we then route it into the root cause analysis module. And the development of this module turns out that variational autoencoders can also learn causal structure in the data, provided that we give them causal cues along with the variables, and we also introduce some masking layers to implement these variable dependencies. In our case, we didn't have these kind of examples. It was a purely exploratory endeavor, but we could still make use of the algorithms from the area of causal discovery to have an idea of the causal structure that was likely to be learned in our environment. And this is what we show there on the right. Those are the 10 most frequent events in our environment, 5 of which belong to the traction system, 5 of which, so the remaining 5 belong to the brake system. That's again the blended braking system. And the orientation of the arrows is what already gives us some useful information. And what we read on the diagram is that the cause-effect relationship that is established for these events occurs from the brake system to the traction system. So root causes in the traction are to be found in the brake, at least for these most frequent events. Obviously, if we had taken different variables, the results could have changed, and also if we challenged the set of assumptions that we took for building that we might get some different results. In this case, we had a multivariate setting, so we solved that with conditional independence tests. That is a Markov equivalence class. We also discretized the time and evaluated the impact of different time lags, but what we got, at least, is meaningful from an engineering perspective and is therefore valuable information to provide to the customers. And before I bring my talk to a close, I would like to highlight some challenges and opportunities as key takeaways. Regarding the challenges, I like to say that the knowledge in the field of causality is very fragmented, and this is a problem, creates a lot of confusion. In terms of inference, we have the potential outcomes framework, we have the DAG framework. Scientists that are proponents of one approach don't want to hear what scientists that are proponents of the other approach have to say. This is all a bit of a mess. And then we have the discovery part, which seems to be a world completely apart. And I feel that given that discovery has its origin in philosophy, such decisions don't want to hear about that. They despise those kind of algorithms. And truth be told, engineers that are concerned with getting things done and delivering something useful can really benefit from this kind of algorithms, because the experts that could provide all this knowledge about the relationships among the variables can't simply make the time to sit at the table and go through all this. So this is a kind of a good solution to get the problem solved. And regarding the generalizability of the solution, that's also one of our challenges, because the kind of products that we build eventually get deployed all over the world. So the assets get subject to different stress conditions. So if we're able to extrapolate and transport the outcomes from one setting to the other, that is advantageous for us. And also, solutions might be developed in one end of the world, but the production is typically delocalized close to the geographical area where the asset is to be used, which eventually introduces some dependencies with the local suppliers that also end up changing that original design. So at the end of the day, we end up with many different models that are similar but not exactly the same. So we have to be careful when drawing any extrapolations. And regarding the opportunities, I'd like to say that causal inference is a very dynamic field in full blossom within the AI community, which is great for attracting talent in data science. It has a great capacity to adapt to change, which makes perfect sense in the evolutionary nature of the world, and the return of its investment is driven by many different factors. I will briefly mention financial factors. We reviewed some of the typical business cases for predictive maintenance, and then there are safety factors, obviously, and there may be many others. So, to me, causality is kind of a great science to adopt today, and I am sure that it will help us build a better tomorrow. And at some point in the talk, I said I would try to build a convincing case for using causality in a predictive environment despite of this contradictory meaning, but did I do a good job to convince you? Thank you.
Great. Thank you very much for that talk. And I think that next to last slide that you were showing is something that's just universally applicable. I think we could all poach that slide and use it for all of our presentations in the future. So really, really thank you for all of that. Are there any questions?
Thank you.
We have one right here in the middle.
Thanks for the talk. The first use case you had, that was the embeddings use case. You're ingesting...
That one? Language one?
Yeah. So here it ingested problem reports and created these word embeddings that are like points of failure to get to the root cause, or can you speak more to this use case a little bit?
Yeah, in this case, the return experience records contain both the root causes and the solutions, but we here focus the attention on the root causes. So we learn them by drawing that association from the problems to the root cause. That is the diagnosis direction in the model. But we also introduce the local context of the project to adjust for any confounding, because that is the way the data was given to us. So we know that the associations, the entailment of the text has that causal structure, so we obviously had to take that into account in order not to get biased embeddings or things like that. Yeah. So this is what kind of work in progress. These are some of the initial steps in this domain, but I think it already gives us promising results. So we'll continue to work on these, and you're probably going to see more about this in the near future. Yeah. Thank you for your question.
Okay, so I think your use cases are super powerful. The second one.
Second one.
No? So in this one, my question is more on interpretability, right? You're trying to get to...
And what, please repeat?
Interpretability.
Interpretability, okay.
So did you lose that? Did you lose interpretability in this approach?
Well, in this case, we kind of have two levels of interpretability, and we wanted to highlight the limitations of doing a straightforward sensitivity analysis, when you take the autoencoder and you just activate some of the inputs and see the impact on the outputs. But this is mainly driven by correlations. So we wanted to compare that with the kind of information that the causal diagram provides, because that is evident, which variable relates to what. Obviously, we have to accept the limitations of the techniques, but to me it's okay. I mean, that is not perfect. I think we've discussed this topic many times during the conference. We don't need the solutions to be perfect. We need to get the customers from the positions they are today to a better position tomorrow. So as soon as we have something to add value to their business, we can ship what we have.
Thanks.
Yep.
So again, on this use case, you mentioned that you investigate the structure of the latent space to perform some causal discovery. So the question is, do you perform this causal discovery on the latent space or on the feature space, or I mean on the variables, on the observed variables? And if you do it in the observed variables, what kind of mapping do you have to translate some structure in the latent space to the observed space?
Well, the learning occurred in the data space. So when I think what you mean the feature space, to me the feature space is the manifold, because that is where the learned thing is. But we did that in the data. In the end, it's an autoencoder. So the inputs of this autoencoder had convolutional layers, because we arranged the data in grids. So we had in one axis the frequency of the events, and in the other the time. In the end, if we chop that and we put in a long stack, we have kind of a very long time series. In this case, the data was or comprised all the events for whole fleet for 1 year. So that was a lot of data. So it was a very long time series. And based on that, we simply gave that to the algorithm to learn how a causal structure could be learned from that, taking into account the limitations of the parameters. Did I solve your question? Okay, well, yeah. We can continue discussing about that then. Yeah, thank you.
Any other questions? All right. In that case, let's give one more round of applause. Thank you very much for everything.
Thank you. Thank you, Michael.
All right, so we are nearly in the home stretch here. We have a very, very short, about a 15-minute break right here. We're going to be coming back at about 20 past, and for that, we're going to then join our final speaker of the day, who's going to give us a very inspirational sort of look at what might be coming over the horizon. So you definitely don't want to miss that final talk. I'm super excited about it. Everybody, get a little breather, and we'll be back here soon for the final talk of the day. Thank you very much. All right, we are just about ready to start, so please come into the auditorium. Please come into the auditorium. Thank you. All right. Thank you very much for coming back in. I know it's been a very long day, so congrats on all of you for making it this far. But we are in the final stretch right here. We have just one more speaker, and it is going to be an exciting talk. So, yes, he is the Director of Product at Causal Lens, and he is here to unveil the next stage in the future of decision making. So everybody just please give a nice warm round of applause for Tom Farrant.
Hi everyone. As Michael said, my name's Tom, and really there are two ways to look at this talk. Either I'm doing the graveyard shift, or they saved the best till last. I'll let you decide when I'm done speaking. But today I'm going to talk to you about some of the new capabilities that we have been working on here at Causal Lens. So at Causal Lens, we're obsessed with our mission, which is to help organizations advance their decision making. We believe that organizations today face greater uncertainty, higher velocity, and lower margin for error in the decisions that they're making. But despite these headwinds, there are a number of different tailwinds, such as the growing adoption of analytics and AI tools, as we've kind of touched on the trend quite a few talks and quite a few conversations about generative AI, but also the adoption of data. And so really what we see as one of the key defining competitive advantages over the next sort of few years and decades is the ability for organizations to move from data to decisions. And those that can do this with the greatest efficacy are going to be the ones that succeed. However, navigating this is very, very tricky. And there are a number of different challenges that we hope to tackle when we talk about decision ops. The first is that the majority of analytics and predictive and correlational machine learning techniques today provide you with an understanding of what will happen next, but don't tell you how to act in order to change that outcome or ensure that outcome. This means that you end up with inactionable outputs from all of the work that you're doing. You're not actually answering the business and enterprise questions that you care about. The second piece of this is there's a translation problem. When data scientists report their results to the business, they report them in terms of precision, recall, accuracy. These don't translate. What business leaders care about are ROI, cost savings, revenue generation. We believe that decision ops can help tackle these two problems and offer a path through this maze. So when we think about data decisions, there are kind of three pillars that we build that on here at Causal Lens. The first, and I've touched on this briefly, is recommendations. We think that in order to succeed, you need systems that output actionable recommendations that inform you how to act in the environment that you're working within. We see this, and kind of the way that we contrast this internally between sort of predictive outputs and those from Causal AI, is taking a sporting analogy. If you're a fan of a given sports team, then predictive analytics is perfect because it can tell you how to make the bet in order to maximize your return. It can tell you the most likely outcome of the game you're watching, and so you can get a nice fat payout. But if you're the manager of that sports team, if you're the person wanting to change the outcome of that prediction, you need to understand how to intervene. And so it's a very passive versus an active mindset. And if you're working within that organization, if you're running that business, if you're the manager of the team, you really need these actionable recommendations in order to be effective. The second part of this is actually putting those recommendations into action. So much of the time we've seen machine learning projects fail because they don't get out of the laboratory. One of the key capabilities that we believe is fundamental to actually making these decisions is getting them into the real world. And so we'll talk a little bit about the different integrations and how we think about acting on those in order to do that. And then the final ingredient we have is traction. So we want to understand whether or not our decisions are being effective. We want to understand how we've moved from action to outcome and realized any sort of value and ROI from that. But crucially, we want to understand that traction in terms of the KPIs that we care about, in terms of those ROI numbers, that customer lifetime value. And so we see decision ops as a cyclical piece that helps us move through this recommendation, action, traction loop, allowing us to go from recommendation into an action to attract outcome and measure the performance and attribute that using causal AI. So let's touch on each of these three pillars in a little bit more detail. The first one we're going to look at is recommendation. And fundamentally, and you'll see on the board out there for those in the room, we believe that your enterprise and your organization already runs on causal questions. And you need to make use of causal AI and the associated techniques in order to be able to answer those. We believe that going beyond predictions is the only feasible way of effectively doing this. So let's zoom in on a given example. Let's take a look at customer retention. So what can I do to actually prevent churn in my organization? Let's say now that I'm a churn analyst and I want to understand the actions that I can take to prevent that. Using DecisionOS or using the causal lens technology, we can actually create an application that generates these recommendations. And so we can see here that right at the top, we've got all of the KPIs that I care about as a churn analyst. I can immediately filter for those at risk of churning. And I'm now moving beyond the predictive and correlational analytics by running recourse. I can actually understand the interventions that I want to take in order to prevent these individuals from churning. I can view these results. I can see here that for this first person, I can actually offer them a 17.5% discount, and that will mean that they no longer actually want to leave the organization, or is estimated to not to leave. I can submit this action to a downstream system and also log it with decision ops. So this is just one way of orchestrating this technology, and we can see here the workflow that's just taken place. I've taken data, moved it into a causal model, and generated an actionable recommendation that I've then captured in a downstream system and fed into decision ops. The final piece is to actually capture that as a given outcome. And so in a KPI that I care about, we can actually capture that traction. So how is this working under the covers? How do we actually kind of perform these actions? Well, really it's about orchestration, and that's fundamentally the key word for decision ops. So we've actually defined an action trigger, and this can just be any sort of arbitrary Python logic. We hope to work with customers in the future to actually define these in a much more structured way. But we can then register that to our decision workflow and actually call that trigger on demand. We can then deploy that decision workflow within that application. So that application we saw from our churn analyst before really is just calling that Salesforce trigger whenever someone clicks submit. This makes it a very flexible system, and it means that many different workflow orchestrators can actually be used to call these workflows. And then the final piece is to actually set up that outcome tracker. So again, we define sort of the logic that we would like to perform, and then we schedule that on a case-by-case basis to scrape that downstream system and actually understand whether the action we've taken has converted to a reasonable outcome. So if we return to that workflow we saw before, what we can see is that currently we're working in this decision app sort of environment, but we can rapidly, thanks to the flexibility of the underlying toolkit, roll this into a workflow automation. So we've connected into different enterprise systems, and we could be using Zapier, Make, or NAN to actually be orchestrating these. In a manufacturing example, we might want to use robotic process automation tools like Blue Prism or UiPath in order to actually perform that orchestration. These are just writing data back to the decision ops system that we'll look at in a second. And so, just touching on how we actually measure that traction. The key part is that we're actually intervening to change outcomes here. We're acting in the real world to change the outcomes we want to. So we might be giving a certain cohort of people a discount. We're then going to estimate the counterfactual and actually understand what the difference would have been to our KPIs had we not performed that action. This then ultimately helps us to calculate our decision-making performance. And so we can report back to our business, in terms of the KPIs they care about, how our decision-making performance is going. So let's now move to the decision ops sort of management pane. We're now in the shoes of the VP of Customer Success. They've got a range of different KPIs that they want to kind of optimize and track. And so we can see this all live within this dashboard. If we zoom in first into this customer churn example, we can see along the bottom our decision history, all of the previous decisions that we've made within that application we saw earlier, aggregated and rolled up to an overall view. And then this graph helps us to understand what our decision-making performance is in reality, which is that blocked line, and then the estimates, which are the dotted line into the future. We can also zoom into an individual decision. We can say, what was the performance of this specific action that my analyst took? We can see the KPI impact that that had and the attribution of that. We can see the cost associated with that example. And we can also see whether the kind of status of that outcome. And so that's the sort of foundational framework that we've built thus far with decision ops. There's a long way to go, but where we see this vision going ultimately is scale. So if we think of an organization that has a marketing attribution case, it's very, very likely that the graph and the causal model that they've developed around that they're optimizing using recommendation, action, and traction, is going to feed into their understanding of customer retention, which is the kind of use case we've been looking at throughout today. So there's some sort of causal link and shared subgraph between these two use cases. Now, on the other side of the business, they might be performing manufacturing root cause analysis to understand and help maximize the efficacy of their production lines. This, in turn, could form into supply chain optimization, and you can start to see how all these different use cases kind of connect with one another. Now, both sides of the business could be connected in a pricing and promotion sort of setting. You know, what discounts and promotions should I offer, given I have an excess in my supply chain? And this will then, in turn, impact who I retain as a customer. But fundamentally, what we're building up to is the ability to perform these kind of recommendation, action, and traction actions across your enterprise performance in order to maximize and optimize across a range of different use cases. So as you build up these different causal kind of algorithms and use cases, you can begin to feed into this hierarchical and higher level understanding of how your business is performing. So just to conclude, Decision Ops helps to accelerate your journey from data to decisions. It helps you to move around this recommendation, action, and traction loop. We're in early access now, and so if this kind of talk has piqued your interest, if there are any other sort of avenues you want to explore, please do get in touch. We're looking for partners to help develop this out and work with you in kind of furthering our vision for this. Thank you very much.
Great. Thank you very much for that. It's an interesting vision for the future there. So I'm sure that some people have some questions about that vision right there. So anybody want to ask Tom anything?
Please.
We have some bold people in the front row here.
Thank you. Oh, just a curiosity about the recommendation step.
Yeah.
Do you actually learn the best treatment, for example? Like you learn to recommend, or you just learn the effect and then you base the decision on the effect?
So in the specific example that we saw today, it's using effectively a technique called algorithmic recourse. So we're using our causal model to actually understand the interventions that would be required to push a person over a given decision boundary. In this case, whether they're going to churn or not. And so we're basically performing an optimization over the intervention space to say, these are the interventions that we believe are most likely to result in the outcome that you have.
Okay, okay, perfect. Thanks.
And then...
When you provide the recommendations, through the dashboards and whatever metrics, how often basically is the estimation part separated from the post estimation, from the recommendation part? Like how many times the model is trained as opposed to instead tested, let's say in the post estimation part? Like, is it trained every time, or how often can be set to be trained versus just the post estimation part, the actual recommendations delivery?
Yeah, that's an interesting question. What we found, I think, is that it's very use case dependent. So usually it's driven by the frequency at which the business needs to use that algorithm. So we found that if it's a weekly cadence, then they will want that model when it's needed on that weekly cadence to be being retrained and updated with that data from the previous week as well. If it's more of a real-time basis, obviously that becomes more difficult. We have a number of tools that help you to understand the correctness of fit of that algorithm and therefore flag when you should retrain. But generally it's driven sort of by the business need. Does that answer the question?
During the action step, can you randomize people to a different action so that you can more validly estimate the counterfactual factual difference?
Yeah, so that's not something that we've built into the capabilities as it stands, but that's definitely an area that we've considered and we've looked at expanding out to. I think the randomization impact would have a really strong effect on understanding, getting the true treatment effect and that sort of side of things. So that is something we want to develop in the future. It's not something in the capabilities today.
Thanks. So this is going to be a two-part question. So first is on the recommendation side. Is the current, roadmap, were you able to build additional constraints? Because what you recommend may not be what's feasible or viable for the business to take.
Yeah, so within the recommendation engines that we have today, you can build in those constraints. So you can build in costs, you can build in relative costs of whether one intervention is more expensive to perform in reality than another. And you can also say, what are your actionable variables? So, if you have age as a feature within your data set, obviously you can't intervene to change that. So you can actually add that as an inactionable variable.
Cool, thanks. Second part for the action part. I guess the way you can actually track, because of the insights recommendation level, is aligned with the same granularity for the workflow, right? For the people actually taking action. For a lot of the decision making, I think some of the MMM model, right? They're taking at a very strategic level. How do you track those value? Because those may not be directly translated into something like marketing action that you can actually easily track because you can connect to another API. Like, any thoughts on that? Like more hierarchy, like decision?
Yeah, so there are definitely some decision processes that lend themselves more readily to the attribution that we've described today. I agree that we've kind of gone through quite a straightforward sort of use case. Where we see those more complex interactions occurring, effectively there'll be a combination of your causal graph and your decision model of the world, how you actually enforce those decisions kind of further down the line, and bringing those two together so that you can understand when the outcome of your causal model is produced, or your recommendation, what the process is to actually realize that in the real world. And once you understand that, you can actually sort of begin to kind of attribute the level of confidence that you would assign to the outcome that you see down the line. But fundamentally, what we would kind of ultimately rely on is the correctness of your causal model. So if your causal model, your causal graph, is estimating effects and understands the world very well, then the attribution of that effect should be strongly realized in the real world.
Thanks.
I have a general question. The causal AI helps us basically to make kind of data-informed decision. It helps us, to intervene. So my question is, do you think the leadership, let's say in any organization or company, they will resist the adoption of causal AI? So they will fear that it will replace them? Just in a general question, because basically what a leader in a company or organization does, so they get paid for their decision-making intervention skills. That's it. So if that's what they do, and if causal AI can actually help to replace them, do you think they will resist the adoption of the causal AI?
So I think that if you kind of, I think it's kind of heavily dependent on how you frame the challenge that you're supporting. What we've seen is that it's very unlikely that causal AI fundamentally isn't an automation technology. We're not looking to take tasks off people. We're looking to enhance their productivity and enable them to be more effective in the current roles that they do. So it's not necessarily a challenge that I think we've seen a huge amount. It's more of an additive capability that we're providing to these organizations rather than kind of removing tasks from people.
Hi, I have a problem in the marketing attribution domain. So usually there kind of existing as a lagging factor, meaning we spend like $1 in brand, there may be couple months that result into final sales. Which kind of affect the causal mechanism there. I was wondering how the decision OS or causal AI here can handle or learn the lagging factor in that mechanism, because that can be like a dynamic. For example, a brand commercial probably have a longer pack impact, influencing the following months the final sales, while some kind of a division or more campaign kind of a advertisement may impact a shorter term period. So that can be also a factor to learn in the model.
Yeah, so I think the causal platform that we have has very strong time series capabilities, and so we can support effectively modeling of those time series or those time effects across different timestamps, and building a causal model across those different timestamps whereby you can account for those lagging effects. You can actually add decays, you can add different weights to account for the different sort of impact of effects over time. So that's absolutely something that we can account for within the platform by building these time series causal graphs.
All right. If there aren't any more questions, let's do one more round of applause for Tom and thank him for his presentation. All right. Well, thank you very much. That brings us nearly to the conclusion of the day here today. The last thing that I just want to do is just do a few more rounds of thanks for all of the people who have come together to make this event possible. So first things first, let's do one more round of applause for all of the speakers that we've had here today. I think they did a fantastic job talking about all aspects of causality. It's been great. So in addition to thanking the speakers, let's do another quick round of applause again for the team here at Levant, the people who have kept us sheltered, fed, and watered throughout the day. I think they've done a great job, too. Another round of thanks, then, for some of the people who have kept all of this AV equipment running and allowing all of us to be heard throughout the day. So that is Gary, Joey, Kyle, Matt, and Zoe, just for all of the organizational and efforts that they've put into place to make this run seamlessly. Also, we should definitely be thanking one person who's been organizing all of this for the last several months, it feels like. And yeah, it's been just a huge success. So let's just all give a big round of applause for Alejo. Where is he anyway? There he is. So thank you, Alejo. And last but not least, the final round of thanks that I want to say is thank you to all of you who have been attending. It's your attention, your focus, and your questions that have really made this event the success that it's been. So from the bottom of my heart, I want to say thank you to all of you. And as a sign of our gratitude, we hope that you will join us for refreshments after in the back room here. So thank you very much to all of you attendees. And that concludes the conference.